kind of a nudge in the direction. They're generally done with the cooperation of member states, and you will have mandatory, so the legislation is drafted in the EU, but they have to be transposed nationally, and usually is a clock. They have to, so the national governments then have to implement that law. If they don't implement it by the deadline, that law has direct effect in the country. So, so there's this carrot and stick. The reason why it's useful is you can have, it gives, the nice thing about directives is it gives member states discretion to go further than the directive, and do other things that they want to do. So it gives the member states a little bit of wiggle room to implement. Like for instance, in the data retention directive in Ireland, it was struck down by Germany, thanks for that, guys. We do appreciate the German court's decision on that one. But the data retention directive was minimum 6 months. In Ireland, they said, oh, we're going to implement it, we're going to do it in 2 years. So that was the kind of, so that was the very member state kind of control. There was a mandatory limit, and then there was obviously the member states were free to increase it if they wanted, just as long as the basic principles agreed at European level were already implemented. Regulations, they're set by the EU, they have a much direct effect, they're much more, they have an immediate and direct effect, and they're usually big deals. GDPR, massive pain in all of our asses, that one was a regulation. And so you can see various different ones. So in terms of examples of communications, we've got state aid for broadband networks. I did actually mention that already. Directives, the European Electronic Consumer Communications Code, so the ECC, is basically a set of regulations to try and help member states regulate the telecom sector in each country. This one was the Network Information Security Directive version 1, and this 2 is a much bigger, broader range of it, and it's a welcome. There's a lot of good stuff in it, but it means that there's a lot more demands put on small businesses in critical sectors. So, for instance, if you're in aerospace, defence, you would have been in that before, but now it's like things like water, healthcare. So if you're in mission critical industries that affect the consumer or the citizen, then you will have you'll have obligations to implement security measures to protect the interests of the citizens who use your services. And so it's becoming a much more wider brief. And of course, we've got the Cybersecurity Act. There's some, there will be implications for the open source community there in terms of, how do we certify security of products, how do we certify the security of the software and stuff like that. There's these obligations, and who's paying for that? And so what I'd be saying there is we need to answer the question as a community, who pays for that? And how can we engage with the authorities so that people can see that the transparency of BSD and the open source, the open development model that BSD has is in ways a certification in itself. It's like a challenge. It's like find the problem here, it's there. And so we need to just inform the Commission more and policymakers more. Because what will happen is, what you often have is, you'll have an implemented act, but then by the time it gets to the member state to be actually fully implemented or enforced, they work with the community to say what works. So no one wants to, so sometimes there's laws created and they're like, okay, but how do we actually enforce this? Or, because you've got a lot of politicians or officials who are not necessarily up to speed in what we're doing, we're experts in ourselves. And so we have to work with them to say, well, this is the best practices we think we should be going to, and this is what we would like you to be looking at. So that's the EU and U. So what happened with me, the start of my journey is I befriended a lawyer and he suggested I read this document, which is the communication from the Commission. It's the EU guidelines for the application of state aid rules in relation to the rapid deployment of broadband networks. And it's Times New Roman, 12 points. It's a lot of text. And my challenge was, he said, point out your favourite paragraph. And just so you know member states have to do everything in that, and if they miss any of it, then technically it would be unlawful. So I looked at this and was like, okay, this is interesting, and then I got a book. And just a tip from, if you're ever reading this stuff, and because I know some of you are very bright and intelligent, more intelligent than me, a lot more, it's not hard, but the key thing is when you actually see a footnote or a reference in any of these documents, you stop, you read the footnote, the reference, you understand it, and then go back and continue reading. So it's very important that when you see any new legislation and you see a superscript number, click on that number, read what they're referring to, so that then you'll understand the context of that paragraph. It really will help illuminate what we're actually trying to do. We discussed the guidelines, and of course we saw the practice, procedure versus practice in Ireland ad nauseum. And the Irish authorities were intervening in the Irish market, so they wanted to give broadband to everyone in Northern Ireland. Great, everyone, that's fine. It's a noble idea, but the objectives or the rules in the guidelines were saying, look, you measure the problem, then you solve the problem. Okay? And you measure the problem is that if someone else is already providing broadband, you don't intervene. Because what happened with my business was I was intervening wirelessly. I was giving about 200 megs to customers, and the government hired these very eminent consultants who said, according to their estimations, we can't deliver 30 megs without ever testing this. So of course this is why I started to engage with the EU and stuff like that. And what is nice is there is checks and balances. So I said, well, the government's not treating me fair, they're overbuilding my network of state aid competition, and so I wanted to tell the EU the truth about what was happening and what we were doing. And so that was what started. And civil servants sometimes can be a little bit cynical, and many of you who I do suggest you watch, there's a particularly hilarious one about Brexit. This is Westminster, it's a British sitcom from the 80s, but it's absolutely hilarious. But I have met with political staff and politicians, and they went, it's scarily, and it seems to be well informed, let's just say. But this guy is Sir Humphreys, and he's quite a cynical, very intelligent man, and runs rings around Minster. But he does talk quite eloquently about. There's one about obfuscation, which is brilliant, because it uses even native English speakers, but he also talks about Brexit as well. I used to joke that I said, look, it took, when Brexit negotiations were taking a long time, I said, I'm sorry for my British friends here in the audience, but I said, look, it took them, say, 800 years to get them out of Ireland, which was going to take them 800 years to get out of Europe fully. So I say, okay, the EU might be able to help me. How do I do it? Well, I wrote to the Director General of Competition, Unit C4, and I began a 5-year journey. It was a right-year letter, which basically means that it was a legal thing, which basically you say what you're complaining about, you say the aid measure, you tell them why you think you're standing, and then that becomes kind of like an informal complaint. And then there's market information, which is, by the way, so the Commission, the EU Commission has exclusive, like they have the ultimate power in terms of controlling or protecting the internal market. And so by giving them that information, they have a duty of constant vigilance to protect the internal market, to protect the fair play, and generally they do that. So that's the importance of it, you know. So I would then ended up making a formal complaint to the Commission, and because too long didn't read version was the government didn't recognise the network, we're overbuilding, wasting taxpayers' money, and creating unfair competition. And I'm now representing about 20 small ISPs in Brussels with formal complaints about that. And the idea, the sad thing I suppose what I would say is, as a small business, I set about trying to achieve what the government was setting out to achieve, but in a wildly different way. And instead of being seen as part of the solution to the problem, we were labelled as part of the problem with that. nothing worse, nothing would motivate me more than telling me I can't do my job. It's like, you can't do that. I was like, oh, yeah. So, the other thing, just to explain who can help when you have some problems like this, and who can help BSD going forward, is look at the commission service. So in any given area, is it privacy, that's data protection, that would be justice, justice commissioner. If it's competition or markets related, it would be DG Comp and DG Connect, if it's digital media as well. So DG Competition under President Vice Dyer until the end of October, and DG Connect would have been under the Internal Market Commissioner, who was Gary Breton up until Monday. It's kind of sad because a lot of people kind of started giving out about him when he left office or when he resigned, and they're all like, keep their powder dry while he was in office, and it's kind of debating whether I throw a few punches at him metaphorically from the stage, but I don't like doing it when he's gone. There's no point really. But then there's DG Grove, which is for small businesses, and that's an important one. And again, it's under the Internal Market Commissioner, which is kind of ironic because the President is very pro big telecoms companies and not so much for. And even like the signalling for buses recently, this is the danger, is that you have people who talk enough about we have too many telco companies and this is affecting service for customers in Europe, and we should be more like America. And I don't know if you've visited North America, but sometimes you think that from the telcos you need more than 3 companies competing in an area to actually get good service. And that's, so there's this, but it's a constant drip feed of BS that something then finds its way into a commission document for a strategy for 5 years, and then you spend 5 years fighting it. So it's the important thing is to engage early, engage often, and just correct the record, In terms of the wonderful thing about the EU is they are ridiculously transparent. They're transparent to a fault theory, but they have organizational charts. So if you want to find out who to talk to, you would look, this is DG Comp's organization chart as of 16. Check it regularly, like if you're going to Brussels, maybe check it because you might be meeting a different person. But and in terms of for internet and software, that green box is where it's at. And they have been the group of people or the units that I've been engaging with, both from an ISP point of view, but also a general internet health point of view. So for the record, I'm a small ISP. I think network fees is an awful idea. I think it's bad for the internet, the health of the internet, the openness of the internet, and I think it's also I think as a small ISP, my job is to connect people as fast as possible to the internet, wherever they want to go. It's not for me to get a piece of the action because someone else sells media services over it or self-managed it. And I think ultimately consumers should be allowed to pay and differentiate between different ISPs based on price, and the price that they pay as opposed to subsidies from government or subsidies from bigger media companies subsidizing local providers. And so this is so I've actually, on the network fees issue, I've dealt with pretty much competency 1, so that's electronic communications, and Antonine, she's a fantastic lady. I've met with competency 3, Bryce Albert, who's been very helpful, and he's antitrust internet and consumer electronics. And then competency 4, I've been their pen pal for 5 years. Sorry, guys, but that's to them. But to be fair, one thing I will say is you're not always going to agree with the EU officials. But what I will say is if you write reasonably coherently, you try, they will actually. You may not agree today, but you could agree further down the line. And they do generally try to do the right thing, with the political constraints that they're operating. And that has been my experience. And so what I would say to people is rather than bemoan the EU is actually engage with us. And if you can tell them, I told you so at Becco, at least you told them so, but you can't complain about something that you didn't engage in as a citizen or as a, and my experience has been, as a small company, like 3,000 subscribers, less than 20 employees, dealing with a file that's relevant and a letter that's relevant, they will meet you. And I found that, I found that kind of humbling when you're talking with a guy who's dealing with policy for 450 million people that can sit down and listen to someone with an accent and Tipperary like me, you know. But the other thing I would say is the policy formation, if you ever want to see, particularly this is useful if the policies aren't going your way, is refit, is the regulatory, is the better regulation. What's great about the EU is the documentation and how they update their documentation. But it's very transparent. One of the key things is the impact assessment. And one of the things I would say in hindsight that was critical, and I didn't engage with at the time, which was about software development, was that they said that the burden of the cyber security regulation would be offset by the increased trust that consumers will have in the businesses. And the thing that I would be maybe slightly critical of is that generally, if you're a small business, the trust you have with the end customer is that personal trust, the delivery service, the integrity of which you deliver. And so sometimes the offsetting measures that we use are not that practical. So, and refit is about one in, one out principle. So what they try to do is tell you, okay, we're going to make life a little bit harder for you here, but we're going to reduce regulation on you here. That's what's going to happen. And that balancing act can be quite, it's critical that that's done fairly. So if you kind of say, we're going to put a load of cyber security regulations on you, and your customers are going to trust you more, you're welcome. So it's kind of, that type of balancing is not as good as we would like. But then there are other ones where they will actually, they do actually try to offset like with grants and stuff like that. But the impact assessment is crucial, and you can engage with the regulatory impact. Forget the term, but it's in the regulatory toolbox. It's basically where the impact assessment has to be realistic. And in the parliamentary committees, they will actually, the trilogue, which is basically a conversation between the member states, the parliament, and the commission. So there's not a dialogue, a trilogue. And when they're actually just finalising legislation and amending legislation, that conversation is had. And if you're calling out bad impact assessments, that's useful. And you're the experts, so it's incumbent on you guys and you girls to actually deliver that knowledge to the policymakers. If you want to get information on how to engage, ask the EU as a free service, and you will actually get legal advice from lawyers who are paid by the commissions. You can also write to the DG Commission, the DG COPS, if it's anyway relevant. Try and use the organisational charts. Try and use the political, try and use if you look at the website for Commissioner Vestager, you'll see her team, or Commissioner Breton back in the day, you'll see the people who are advising him or who's dealing with from a political point of view. So the Commission is kind of unusual in that you have services, that's a permanent civil service that you deal with, but you also have the political leadership of the Commission. So on stuff that's been discussed politically, you should engage politically, and then on in terms of procedural rights and procedural entitlements that you have, or often what will happen is the Commission will say, we want to change these rules because we think they're out of date. What do you think of them so far? What should we do? And there's and I'll get to that in another slide, but that survey is really useful. It's have your say from the EU, and you can actually sign up and say, I'm interested in digital rights, I'm interested in internet, software, antitrust, stuff like that. Stuff, whatever, training, knowledge, you can put that in, and then when they're actually trying to do an initiative, they'll ask your opinion. And it does have an effect. They do try to take it into account. Like one of the interesting things I found was when I dealt with the state aid complaint, it was on the 2013 guidelines, okay, so it was ages ago, right? But then they said, okay, we want to revise it because modern technology, believe it or not, has moved on in the past 10 years. 5 minutes, yeah? Okay, perfect. So the modern technology moved on, so they wanted to revise and see how it was going. They'd done it for 10 years or 8 years at the time. So But then we were talking about the issue of countries basically gerrymandering the rules so that it would be like a high jump that there's never a bar, and you're told just run up and jump, there's no bar, and then you jump, you go, sit naked, sorry. You know, so, and that type of issue where you can manipulate the rules so you can assess the market and say, just no one's here, it's just magic. That was the issue, and in fairness, when they put that in as an issue, even though it was a minority submission, they considered it reasonably significant that was something that needed to be dealt with. And so the 2023 guidelines, I'm pleased to say that there was a lot more rigorous analysis of what was required to technically assess an ISP, which is good. It's great for the system because it means it stops small ISPs or bigger ISPs being opportunistic, saying, oh, we can give it to everyone, and they only give 100 legs or something like that. So there's a fairness there. And it raises a small business. If the internal market is fair, we're winning. Like that, we can compete in fair markets. It's when it's stacked against you. And that's why many of these policies which have great intentions, but there's often the unintended consequences. And if you're not there watching that, you're set to lose out. You can sign up to the transparency register. It's really good. And you can also sign up to have your say. So have your say, they'll email you all the time and say that, oh, we're doing a survey about state aid, we're doing a survey. And it's really useful. The transparency register is good because you're basically setting out your stall. And people who might be interested, 3 minutes, perfect. So, I will just wrap up with that and just say, just engage early, engage often, support your foundation. I got to be introduced to the previous foundation. I think their engagement, with people and on LinkedIn is excellent. I really appreciate what the EuroBSD Foundation does in support of the EuroBSD Foundation community, or the community of the EuroBSD. And what I'd like to see is more of, I suppose, that engagement with politicians, particularly you, because there is a trickle-down effect where the ideas, good or bad indeed, will sometimes leak out to other countries. Like, for instance, network fees became such a big thing in Europe for 5 years, and hopefully it can be put to bed. But in America, it actually then got reignited again. And so they're the bad ideas, but then there's a lot of good ideas like roll out broadband to improving access to the internet, improving cybersecurity. And it's like, can we get BSD as a community to benefit from these ideas, and can we contribute it so that the ideas are better executed in Brussels? That's the key thing. Thank you very much.
All right. Well, thank our speaker. Any questions? We've got about a minute for that.
Any questions? I don't bite, I promise.
All right. Well, Tom will be here all weekend, so let's thank our speaker again, and from the organizers, next up in a few moments is Franco on his previously tooling. Franco, are you here? Right. And I'll probably need to take the mics off you.
No, I'm keeping the mics. Thanks very much. That's the recording one. And if you like the naked gun, where he goes to the bathroom.
further questions?
I think you should probably try to aim for somewhere between 5 and 10 minutes of questions. But there wasn't. Do we have anything to do with the PA? Oh, that's all the time, isn't it? Looks like the streaming mic is off, so we need to use this one.
Okay, so we do have a lot of instant feedback whenever we release something, which is a good thing. We have model view controllers, things that translate to APIs that you can use for automation, and we have a big plugins collection as well. There's it's a scripting language most of the time, which is PHP, Python, and POSIX. And we try to stay as close to FreeBSD as possible, which isn't always possible, but we still try it as an aim, and it will come up later in the talk a couple of times. We have 2 fixed major releases per year, which is something that we really enjoy, and it's also nice to see that coming to FreeBSD in the future. And it's a bi-weekly stable update cycle. Sometimes it's 1 week, sometimes it's 3 weeks. So that's just because there are some issues with security packages, OpenSSL, something like this, that may require immediate attention, or it's a little quieter. But on average, it's, every 2 weeks. We do the Suricata integration, which also has NetMap support. And obviously, we do the port maintenance there. Lately, we also ported the OpenBSD DHC relay to FreeBSD, and it works quite well. And everybody knows the ISC is end of life. So that might be a nice replacement for everybody who's looking into this. And there's actually a PR at Bugzilla if somebody helps with bringing this to FreeBSD ports. And also, we are maintaining a DHCP 6C client, which is from the widely known white DHCP v6 package. And that's something that people for Orange France needed, they said, well, we have a custom patch set, can you look at it? And then we had to integrate it. And then afterwards, more people came in and said, hey, I have this IPv6 problem, can you look at it? And so we've slowly started maintaining that, and it's a good project from our end. And about this talk in particular, I just want to give some information and entertain. It's not very in-depth technical, but it will cover a lot of ground. It's just a case study, not an how-to guide, and it's also not chronological. I try to do that, but it makes more sense to present this in a logical order. Yes, so basically what this is OpenSense solutions to FreeBSD challenges, but not in the sense that FreeBSD has these challenges, just the things that are not there that you need in order to do a distribution of the size of OpenSense. And of course, the benefits of FreeBSD from these challenges are things like bug reports and also some of the tools that may be used there as well in the future. And the talk is available at this address already. So, let's go. Imagine it's 2015, January. We've been working on OpenSense for, I think, 2 months to get it ready and out. There was a first release. And back then, Pudria was still very young. Package NG, as the cool kids called it back then, was gaining traction, but it was not in the code that we had. Quarterly packages did not exist. Package base was nowhere to be found. And looking back at this particularly, a lot of great work went into this in the last decade. So I'm looking forward to seeing this soon. And FreeBSD still used SVN, and the PSense code already used Git. So we had a little bit of a problem with the integration in general. So the actual scope that we had was a base and a kernel, hundreds of packages, direct and indirect dependencies, and of course, custom packages and several images. The source and the ports patches, they were actually not separate trees. They were just patches that lived in the build directories, and it was quite difficult to maintain patches, especially when you had diffs of patches that you needed to review, and so on and so forth. So something needed to be found to make this more manageable. It also had interactions with the build system, which wasn't great because it could end up destroying images or updates just because some files got lost on the base system. And also the build tools were using FreeBSD. Does anybody remember FreeBSD? Okay, great. So the last release was in 2007 already, and there was nobody around who could tell us how it works, so we thought about replacing it. And then basically the motivation that we had was we want something that's easy to use, traceable, change-rooted, safe point-based, and of course open and available for everyone to use. What we ended up doing was minimal shell scripting around the existing source and ports repositories, just because we still needed something to manage the whole process from getting something compiled to building an image at the end. So we had to rewrite the build tools from scratch to avoid FreeBSD, which is going to be important a little bit later, and use Git exclusively and fill the gap with Git SVN if necessary. And I do remember a good colleague of mine in the past who said Git is horrible, but the SVN client is pretty good. So that's something that stuck with me, and that's also where we wanted to go. Obviously, we want to use package as the main tool, both for building the images as well as updating the systems. And we also want to handle a subset of the ports to maintain the things that we do actively use, but then again, also sync the rest of the port tree just in case somebody has interest in getting a port from there instead of just going to the FreeBSD port and then end up handling 2 ports at the same time. Yeah, and all of this, the idea was to have a fast deployment and testing cycle. Right now, this says user base, testing with the user base, which requires more user-facing tools. Back then, it was just something that was nice to have in the sense that we do want something where we, as developers, can quickly apply a patch that we have written between us, or test a kernel, test an idea, embed it into an image just to see how it works and so on and so forth. But it quickly transformed into something that users could really use to well, to give feedback on components and problems that may arise from updating them. And just quickly, the terminology itself. When I talk about the tools, it's the build tools that glue everything together. The sources are the modified FreeBSD sources. Ports are also slightly modified. There are a lot of reasons for this, but it's very difficult to put this all into the context of just this talk. The core system is the thing that provides the functional GUI and also backend parts to boot up the system, to be configured over the GUI, over an API, and so on, and basically to use it as a firewall and a networking device. And the plugins are also important because the plugins would allow to extend the scope of the core project itself. Some of the things, they were always part of core, but we had to move them out of the core. And then there were people coming in, for example, they wanted bind, so they were integrating bind as a plugin. And you can also use plugins for zero config things like the CPU microcode packages, for example, where you just install the plugin, it pulls the dependency and sets up the configuration for you, and then you just have to reboot in order to activate it. And also what's important about the plugins is that if somebody wants to have a private thing just for themselves, they can do that and install it in a stock system. And also for commercial purposes, plugins are great. So all of this is allowed and accepted and nice to have. And everything that I talk about here, you can find on our GitHub. So, what happened? What happened was that we ended up rewriting the build tools. And well, the fun thing was we ended up using makefile dependencies, which is exactly what FreeBSD was doing. So we figured out how it worked and then liked it so much that we used the whole idea of it to build it up from scratch. And the shell scripts underneath those dependencies, so the dependencies are, you have a base system, you have a kernel, then you have the ports, and then you have the plugins and the packages, and each step is then calling the next step, so that you also have save points with regard to, you already built the kernel, you don't have to go back and build the kernel unless you change the kernel sources, for example. I also want the tools to hold custom configurations across different versions and all of these things. And we want to use individual build steps also to build, well, to do different kinds of builds. For example, when you hotfix something, you want to replace a port because it has a port vulnerability, and you can just take those individual steps and build something arbitrary with them. That's also a nice thing, and the nightly build works in the same way, for example. Yeah, reuse progress, provide rebuild components for fast and custom image build, and of course document it. Yeah, that's what we did. And just to illustrate how it works, you take a stock FreeBSD, you install Git, you get the tools repository, the make update call will update all the repositories and clone them if they're not there. And when you want a DVD image, you just type make DVD and then you wait, I think 10 or 12 hours. Yes, but we get to that. So, side quest time. We quickly realized we needed more glue to hold everything together. So package upgrade updates the packages, but we still need to handle more things like alternative core packages, which means you have a community package, a business package, and a development package. And right now there's a package vital flag, for example, and you cannot install something if something has a package vital flag. So you actually need to write some glue in order to change from one type of core repository to another. We also want to emulate FreeBSD update. but created with standard FreeBSD targets, but we didn't know what that meant at the time. But we get to that. Cross-ABI update compatibility, of course, but offline. That's pretty interesting because a lot can go wrong if you rely on the internet in order to update something. So what the OpenSense update actually does is it downloads the base, the kernel, and all of the packages, and then it reboots multiple times in order to do everything that you know from FreeBSD update, but you don't have to do any user interaction in that case. Right, like the package upgrade F that you need to do after a major release, it's just something that the tool will do for you. To that end, the package mirror also has the latest link, as people know, but it also offers directory access to every stable release that we have, which means you can actually do targeted updates to older releases, to known good releases. And since we only have a subset of ports that we publish, it's about 700 or 800 megabytes. That's something that we can get away with. But if you have 22,000 ports, that's not possible. And there's just some examples. You can add a debug kernel from the snapshots. You can do a whole major upgrade. That's actually all you need to do with a -u. And there's a hints file which says what the next kernel, what the next major upgrade is going to be. And then OpenSense update BKP just means base, kernel, and packages, which is a normal minor upgrade in that case, doing everything at the same time. Yeah, and then came the source tree. And we decided quickly that we wanted to reuse the base and the kernel sets as the primary source for these components. And we do have some modifications for different reasons. And one of them is that we want to update some components via ports and not have them in the base system. So we took out Kerberos, Unbound, OpenSSH, OpenSSL. That's still in the base system, but we prefer to use the port. And that actually helped us a little bit when we went from, well, we were still on FreeBSD 13.2, but we wanted OpenSSL 3, so that was the easy way to get both of these things in the same release. The kernel's built on top of generic, which wasn't always that way, but we tried to be as close as possible, as I said. We have some modifications for RSS to make it configurable at runtime or at boot time. I'm not exactly sure. That may be interesting to FreeBSD in the future. And we also have a couple of drivers that are in the kernel configuration for legacy reasons. And then the question arose, well, but what do we do to verify what we're actually downloading and installing? That's going to come up in a bit. And for now, we also wanted embedded version and build metadata. We needed a way to handle obsolete files. We also wanted debug kernels with automatic handling, which just means that normally the kernel's in text dump mode, but if somebody installs a debug kernel, then it will automatically reconfigure to do core dumps, just to not have people struggle with the fact of how do they configure this. And then they can send us a core dump and we can look at it. Oops. So then came the next side quest. How do we do signatures? And there was something ominous called package txz.zig. And that's part of the package bootstrap process. And then we thought, well, why not take this code and make it verify arbitrary files? And so we have two scripts. One creates signatures and the fingerprints for the package signatures. And then it just hooks into the fingerprints of the active package repository. So when you download a kernel file now and you download the signature, it's on the bottom you can see you just use OpenSense verify and the signature lies next to it. Then if the return value is good, then it's verified. And the really nice thing about this is that we hook directly into the package repository file, which has a fingerprint. So we don't have to do any sort of configuration except to rotate the key for each release. That's pretty neat. And then, of course, use it in OpenSense Update. So we had this problem out of the way. Then the ports tree, we needed a way to use Git, but there was a repository copy, but then we decided we don't want to use a full copy because we don't always know what are good updates and what are bad updates to ports. So we wrote something that's called Skim, which is a tool that works on a ports config file, and it goes by port, and it figures out all the dependencies, and it figures out all the build dependencies, and then it tries to sync every directory, and it shows a diff of the directory between the FreeBSD tree and our tree, so we can cherry pick which changes we want and which changes we better leave out for now. And that works pretty well, but it does bring the ports repository in a out of sync state for some components. And we also thought about doing Git merges or Git cherry pick, but the merges have the issue. If you merge a certain commit from the ports tree, you get all the history below that. And if you do cherry picking in the ports tree, then you can spend the whole day cherry picking the changes. Okay. So then we built the ports, retain the package progress, only keep the relevant packages, so the build dependencies go, except these are build dependencies that are going to be reused a lot, like gmake or cmake. And then there's Go and Rust. Go itself is not a problem. It builds really fast, but it still adds about 100, 150 megabytes to the repository. And if we try to stay at 700, 800 megabytes, we don't want to add Go to the packages. So we did something that's called auxiliary packages, which is just a different set that's beside the packages set in order to keep those packages. Because the problem is Rust in this case. It's also big, but it takes a very long time to build. And if you need to go back and rebuild ClemAV, for example, or Suricata, then it will take the better half of a day to get there, if you can even do it on a dev machine. Yep. And then we also have a disk file cache, because we saw very early that if you run a build on the ports and it takes about 8 to 10 hours to build everything, and you also want to fetch things, then it's probably going to fail at some point. So fetch all the files first and then do the build steps without fetching anything. Build everything in a clean change root. I think that was also the time, 2015, where it started to do the ports tree started to do the staging, which was helpful in that regard. Yep, and there was also an audit step because it's not trivial if you have a set of packages on the disk and you want to know if they are vulnerable. You needed to write a small script that installs those packages and looks for vulnerabilities. I think that changed recently, but I haven't checked that out yet. Okay, the next side quest, OpenSense Revert. That's basically just something that started to happen because we were actively storing all the versions on the mirror, which means that you can actually revert to a package that you know that may be bad, and you just give it on the bottom a version of an OpenSense release, and then you go back to that package version. And two things are important here. One is that you need the signatures for this, and then also if you know how the latest directory looks like on the package mirror, it just has the package txz and the package txzig. But if you add all the other ports there, then you can use this as is and roll back those packages, all of them, separately. And also it has snapshot support, which we do sometimes. That's never in some sort of release, but it's just much easier to tell people, can you try this development snapshot instead of showing them a binary or asking them to compile something. That usually takes too long. So then we have the custom packages, and some people have asked in the past, why are these not ports? And well, we don't want to have actual code in the ports tree, so you start to do external repositories anyway, and then you're going to start to overcomplicate the build by adding just more external repository references. And plugins, I already talked a little bit about this. The plugins repository itself just looks like a ports repository, to be honest, from the structure, but it only holds the GUI parts and the things that are relevant to OpenSense itself. And the core is also another repository, and we kept the plugins and the core apart for the simple reason because the plugins are also something that the community builds on a lot. And so we can actually give maintainers access rights over there, and the core team will still work on the core. And yeah, of course, accept pull requests and so on, but we just separated those concerns for us. Yes, and both repositories basically are just a thin wrapper around package create, so they can do their own packages. You just run the make package, and then you have those as well for the packages set. And what's also in the ports in the plugins tree is the multiple flavors, which can also be useful. We have called it variants just to avoid the complication with the ports tree in this regard. And then the last side quest. In the beginning I said we have a lot of PHP, a lot of Python, a lot of shell scripts, and having all the patches on GitHub anyway as an open source project, well, the easy thing is just fetch the patch, apply it, maybe do some error handling, and cache the patches. Which means that if in GitHub you view a patch and you append .patch to the URL, you get the raw patch file. Then you can download it, and you can try with patch to apply to the running system. And if it would apply, then you can start applying it. And if it doesn't apply, it will just stop in this case. And the nice thing about patch specifically is that we don't even need to do patch reverts and ask people to test that, because they can patch the original patch. And it will just be reversed. And if they run it twice, that happens sometimes, the system will be back in the state that it was before. And to make that perfectly usable from a user perspective, in case something goes wrong during boot, for example, we cache all those patches. So if you reboot and the box is not up and you don't have internet access, you can still revert the patch in this case. And the limit, obviously, here is patching works only on scripts. Binaries are not in the scope, but there's OpenSense revert for this one. And then just to illustrate, well, there's a core patch in the first one. The default is a core. You can do patching by component, which just means it sets the patch level and some other things in relation to where the files are in the repository and they are in the system. And lately, we also added the zero config, which just takes the full URL and figures out what to do in those cases when it knows the repository where this is coming from. And especially the last one is important for us, because we always want to tell people that's the commit you're going to apply. And then we had to post the link, and we had to post the OpenSense patch, and now we can just post this one line, and people can click it or run it. And it's obviously mean to post that to someone who only has console access, so both options are still good to have. And then the images. We want to build a couple of images. You saw the DVD before. We have an image for serial devices. We have an image for, it's called Nano, for historic reasons, which is the NanoBSD in this case. And there, everything is set up, and you just flash it, and it works. We do have virtual machine images that we can build. We also have a VGA image as well. And users can actually prefetch the sets to build images in case they want to build images. They don't have to go through the whole build process. They just download the 3 sets, the base set, the kernel set, and the packages set. And everything that they need from a standard distribution is already in there. So it only takes 1 or 2 minutes to build an image or to modify an image if that's needed. We also have a Beehive tester for this, which is very handy because then you can test network access from the images, and you can test if they would install if you plug in a disk as well. The images also have signatures. We already covered the signatures. You can compress them, and there's a distribution helper target which basically figures out which version is installed in the sets, build all the images, add the public key, the public signing key as well, and then neatly wrap it into a distribution archive to be published on a mirror, for example. And one use case for this especially is we do have a separate script that does ZFS installs. It's basically a virtual machine image with a default ZFS install, and then you just flash it on the drive, and on the first boot it will expand to the drive size. Okay, now I rushed through all of this. So how do we use this? And there was one case in particular that I thought was interesting to share. So I'm just gonna show you what happened. We did a stable update from point 1 to point 2, and some people were reporting a panic in the AGP subsystem, which was pretty interesting because we didn't change anything about it. And then we thought, wait a minute, there's something strange going on, and the process was zpool. And there was one change that we did. Somebody has figured out that zpool import -a doesn't work since FreeBSD 13. And that is because FreeBSD changed the implementation of ZFS, and in the old implementation, the default was to look for all the devices in def, which it doesn't do on FreeBSD. And then we kind of stumbled upon this by telling it to do the thing that it used to do. And we still had to test that theory, but we had a problem. It was happening during boot. So it was not easy to do OpenSense revert or OpenSense patch in those cases, even though we could have patched it in general. So we ended up building an image for the user to see if it really was this change, and it actually was this change. So he confirmed it with the image that AGP was crashing the ZFS systems, but the impact was very limited in those cases. And then we looked a little bit closer, and when we ran the command in trust, we could see that, well, it opens every device in def to look at what's going on, and if this is a ZFS device, and if it can import this. But yeah, that's what I already said, disabling. And then we disabled AGP in order to verify that it was really this component that's bad, and this also worked. And the best part of this is, so we're talking about AGP, 20-year-old hardware at least, but that wasn't 20-year-old hardware. That was hardware maybe from 10 years ago from some Chinese or Taiwanese company, cheaper stuff, and it was actually serial devices. So disabling AGP didn't matter to those systems. And then that's actually the thing that we did for our release to get out of that situation instead of reverting something that obviously for most people works, which is import all the pools. Then we opened the bug report, and Mark was nice enough to look at it. And we had the user take do a core dump for us, also with the tools that we have. And then we looked at the core dump, and it said, or it kind of looked like a memory corruption in the AGP close, but we didn't know where it was coming from. And well, the working theory in this case was it has to be some sort of AGP driver regression that nobody's seeing because, well, zpool-a is no longer doing the iteration over def in those cases. And then Mark found the problem. It was sort of a memory corruption, with just the wrong pointer to to avoid pointer given to the close function. And the actual commit that changed this behavior was in 2021. So that was a very long time ago. And the funniest thing about this was that Warner, 1 year earlier, asked the question, do we still need this driver? And, well, now we have a fix and the answer to the question.
The answer is no, right?
Correct. Okay, that's it. Thank you for listening.
We still have about 10 minutes for questions. If there are any questions?
Why do you need a graphical driver in a firewall?
We don't. That,
Okay, so why? Do you have some driver on everything, generic kernel in the firewall?
yeah, it's just generic, and AGP is still enabled in the default. Right, but again, these, I think what people had were some sort of LAN boxes or so, smaller 1U network appliances 10 years ago, and they probably had some AGP thing on the chip or somewhere near the chip, and that's what caused FreeBSD to activate it.
Any other questions?
So, Franco, you mentioned package base right at the beginning. How will this change things for you and make things easier, or is it too much of a change on the existing tool that you've implemented an enormous amount of effort on?
It will be a challenge, but I do think it will life a lot easier in the future. We still have to keep most of the things that we have. We also use the signatures, for example, for the images. We use them for some other packages, like we have a changelog repository where we put in all our changelogs, and then we can actually pull that on the box, and then people get the new changelogs, and we can actually also fix typos in older changes that we did, release notes. And for those, we also use the signatures. So all of that is not going away. What is going away in that case is the use of the base and kernel TXZ as an update mechanism. And it's going to be a lot better if we have package base, because then we have more control over the components and see what sort of changed. And also the whole, the bandwidth involved is also a lot smaller then, because it only updates whatever has been changed. So I'm really looking forward to it.
Hi. Just
Hi.
wanted to know then, do you still have then signatures for the patches as well? Or?
For the patches, no. For this, we do trust GitHub and the SSL, TLS tunnel. I did have some chats with GitHub that some things are not ideal for them, because if you do a PR, then you can actually patch from the PR commit, and it doesn't really differentiate between those. So that's certainly a risk, and also why I mentioned that we do want to post the patch link as well, and make sure that people know what they're going to apply. Yeah.
Let's thank our speaker, and as I just token of our appreciation to the organizers.
Oh, thank you.
currently on mute. So
Which one is it?
The top.
The top.
I think if you slide, it will unmute.
I see.
Unmuted, and now it's muted in a
Yes.
second.
Ladies and gentlemen, can I have your attention for our next speaker? Mateusz Piotrowski is going to talk about FreeBSD service scripts.
Thank you. So, hi, thanks for having me. I hope that you have your phones, because today we're dialing into 180 RC help, 8 scripts. So today we're going to learn about the FreeBSD service scripts. And yeah, let's get to it. So we are not going to dive very deeply into the implementation. I won't be reviewing every single function or variable that the subsystem defines. Instead, I want to show you enough of the implementation details that you are feeling comfortable with using it and coming up with solutions to the problems you may want to solve with the RC8 ecosystem. The outline of today's presentation is as follows. We'll start with the booting process, because the RC is an integral part of it. Then we go through the basic usage, the RC8 framework itself, the scripts implementation, configuration, how to write the scripts, debugging scripts, optimizing performance, then a bit about testing and security news, and then the summary. So let's begin. The booting process. So that's roughly how FreeBSD boots. We're skipping like the very early stages of it from the perspective of a user who just uses FreeBSD and not hacks on it like a lot. What you need to know is that the loader loads the kernel, and you can set some kernel environment variables there. And then the loader starts the init, the first process ever that runs on the FreeBSD. And then the init starts our RC scripts, which then start all the services you like to run on your operating system. And here comes the first tip in this presentation. You can actually replace RC script over here. If you want to, you can specify init script and then the path to your own implementation of etcrc. You do it in loader.conf, and this way, if you have a very specialized embedded device, you can remove the whole RC framework and just, run a couple of things that you need to be running on your system. It can be done. It is not recommendable, maybe. It's not recommended because it's a slippery slope. At the beginning, you think like, oh, okay, I'm just gonna run like 5 things, but then it starts growing, and now you are maintaining like a shell script of 2,000 lines on your own. It's and then you have to upgrade, and it's incompatible with like the newest advancements in FreeBSD. It's not a good idea. It's possible, but think twice. The basic usage. So this is something you all probably know. So when you install FreeBSD, you start to enable services, to make the operating system do things for you. So when we look at the example of SSHD, you can enable it in a couple of ways. And by enabling, we mean we tell RC that whenever the system starts, we want the enabled service to start automatically. So the easiest way to enable SSHD in this case is to echo SSHD enable yes to rc.conf. You can also edit this file with a text editor. This is like the simplest way. You can also add this configuration to different configuration files like etc/rc.conf the SSHD, which is very specific to SSHD. We'll learn about it later in the presentation, but the core point is that rc.conf is not the only configuration file we have in FreeBSD. And there are also other ways, a bit more automated for enabling a service. You can ask the service itself to enable itself. You can say etc/rc.the/SSHD enable, and the service will add this SSHD enable line to the configuration file. And the same happens when you run service. The service command, is the same kind of thing. You can also use sysrc for that. So there are many ways to do it, just as an introduction. To restart a service, we either call the service directly using its path, or we use the service command. Very simple, right? Service, the name of the service, and then the action we want to do. There are also many other actions, like we can ask for the status of a service, if it's running or not, what's its PID. We can poll for it. This is a very cool feature. Not too many people know about it. You can, when you run service SSHD poll, you wait for the service to exit. So when you're doing some interactive things, you just stop the service, but you want to wait for it to actually stop before you continue working on other things. You can run service SSHD poll, and then the system will wait and wait and wait, and then will exit when SSHD actually exits. So it's a pretty nice thing to use in scripts or interactively. We also have things like stop, obviously, and if you want to know if a service supports some special commands, you can ask it for it and run service SSHD extra commands, and it will tell you what are the special commands it supports. In case of SSHD, it's config test, key generation, and reload. So the RC8 framework. This is actually a bit of a complicated matter, because when people say RC8, RC framework, they often refer to, it's an overloaded term. It may refer to two different things. One of them is the etc/rc script itself, which is what controls the booting process after init. It runs all the services during boot and handles special configuration setups like diskless booting, right? This is what we discussed earlier in the slides. But there's also the RC framework, so everything that happens to services on FreeBSD. So, it's a common name for all those programs in this ecosystem, and it covers everything from boot to shutdown. Luckily, it's fairly small, so you could probably read the whole source code of all those little utilities in one afternoon and have a good understanding of what's going on there. So now let's take a look at etc/rc implementation. So I removed most of the lines, but I'm just presenting you the most important ones. So at the very beginning, when etc/rc starts, it handles auto-booting, diskless booting. If debugging is enabled, maybe we are booting into a jailed system, so we don't have to care about kernel services and so on. So it handles all of those little things, and then we get to starting the actual services. And we do it in 2 steps. So every step has 2 sub-steps, let's say. First, as you can see in the yellow highlight, we run RC order. This is a little utility that allows us to sort all the services in the order of their dependencies, so that we provide just all the services, their paths, and as a result we get a list of what would be the order of starting them, so that we don't start SSHD before, I don't know, we get the access to, like, I don't know, the file system where users store their shells. And that's what's going on here. We run RC order, we provide all the paths. As a result, we get the files variable, and we provide it then to the run RC scripts command. And in the first case, we have this break flag, which means that we are going to run all the scripts up until a script that we call the early-late divider. So what it means is that we set up the system, we start all the essential services before we start handling all the others. And why do we do it this way? The reason is that the early-late divider is actually the file system's pseudo service. What happens here is that we boot the system, we connect to the network, we mount all the critical file systems and so on, and now we have access to more file systems, right, and the network. So maybe there are more scripts for us waiting on those additional partitions we just mounted. So in the green highlight, this is where we look for those additional services in those new partitions. And now we run RC order again, and we run the rest of the scripts that we, maybe had in the base system already, or maybe that we found on the new partitions. Now we can run all of them because we have, everything ready to start all the services we configured. Regarding the service scripts themselves, this is like the list of all the service files we have in the base system. The highlight in the blue highlight is the file systems service I told you about on the previous slide. And in this example, we also have a couple of services coming from the ports. In this case, on this server, it was only five of them. But it can be much more. Usually, people don't run all of them at the same time on one system, but they provide a lot of functionalities. So then, we have RC order. Let's take a closer look at this one. So when you have RC order, you provide all the paths to all the scripts you want to order. And in this case, we grab for SSHD to see where it lands in this list. And it turns out it lands after the login milestone, which is nice because login means that, okay, at this point, users can start logging in. Everything is ready for them. If they source some files or they require some special utilities in their profiles when they log in, they should be available at this point, right? It's fairly late in the boot process. Everything is ready for the users to log in. And the way RC order achieves that is by having a special RC order block in every service script. It usually has the provide line, the require line, and the keyword. So the provide is just the name of the script, so that we can have an identifier when we order stuff. Require is what this script specifically requires before it can, start. In this case, in case of SSHD, it requires not only login, but also file systems. And the keyword, in this case shutdown, is like a special note to the RC framework saying that, hey, when we are shutting down, stop SSHD specifically. Like, maybe there's some special cleanup procedure, or we just want this service to stop cleanly, but handle it. Don't let it just die when the system is shutting down. The second example on this slide shows how you can verify what would be the ordering of two scripts you're interested in. In this case, it's login and SSHD. You can use grep to select just two of them. And there are just 5 of those placeholders: daemon, file systems, login, networking, and servers. They are all described within their source code, what they actually mean. So if you ever need, to have a milestone, that's what you should look into. And then we have a situation sometimes that we have our own custom service, like SSHD preparer, and we want to run it before SSHD, but we don't want to modify the SSHD daemon, because that would be, sad to modify a stock daemon to add our custom patch. It's a very dirty hack. So RC order handles that by offering us another keyword or line It's called before. So in our custom script, you can say, hey, like, please schedule this service before SSHD. So this way, you can still get the ordering you want without modifying the files in the base system. And then some honorable mentions of many other RC scripts. So those are very custom things. Some of them don't exist by default. The point here is that whenever you have a very specific need to execute some commands, whether it's like, at resume, at suspend, maybe at the final step when all the processes already died, the RC framework allows you to hook into those places. So there are usually ways to do things you want to, and now you know. It's all in the documentation. So scripts implementation. Let's take a look how you implement the scripts. So we are going to start with a very simple one. This one I called a one-off pattern. This one is sysctl, is the sysctl service from the base system. So in the yellow, you see the RC order block. It just says provide sysctl, no requirements. It probably starts very early in the boot because it has no requirements. Very nice. In orange, you have the sourcing of etc RC subroutines. This is like the library for all the RC scripts. So at this point, when we load that, our script is no longer just a script, it's an RC script, and we have access to all the nice functions and variables that we can use to make our RC scripts more declarative and not just like a bunch of shellcode, that is not very maintainable. And then we have things like the name, the description. In green, you can see the actual command that we want to execute in this service. In this case, it has been sysctl. The stop command is very interesting. It's just a colon, which means that if someone decides to stop the sysctl service, nothing's going to happen. We won't get an error, right? But it's a one-off script. It's not a daemon running in the background. It just reads the sysctl conf files, applies the changes, and then, it's gone. So there is no reason to stop it. That's why we call it a one-off pattern. And then we have the start command variable. What it means is that we don't rely on the RC framework to implement the start of the command, on its own. We say that, hey, we want to do like some special things to it, just starting the command is not enough for us, so let us redefine it. So that's what we do in this function sysctl start in the middle of the slide. And I cut out most of it, but essentially we just run the command. There are some checks before that, but essentially we just run sysctl. In pink, you can see that we are loading all the configuration files. We are not sourcing it directly like the rc.conf because there are like many different files we need to source. So we have a helper function for that. And then we run rc, we run the run rc command finally, and that's when the service starts or stops. It starts processing our request. Another pattern. Simple service pattern. So in this case, we talk about inetd, which is a daemon. We start it, it runs, and it's going to run until we stop it. The RC order block is a bit larger this time. We have some requirements, the shutdown keyboard. Cool. In green, you can see RC var that defines the enable variable for this script. So it didn't make any sense to have it for a sysctl, right? Because if you don't want sysctl to configure anything, just don't put anything into sysctl.conf. In this case, we have a specific variable. So if we want to enable this service, we have to set it to yes in our rc.conf. And then again, in blue, we have the command. In pink, we have the PID file. So now when we ask for status or we stop the service, the RC framework is going to know which PID it is, that the service is related to, and will be able to ask for its status or like kill it and so on. And in orange, we define extra commands like reload. So that would be it for writing scripts for now. We also analyze another example later on, but let's focus on configuration now. So most of you probably use etcrc.conf most of the time. This is like the place to put your configuration in. Another important place is etc defaults rc.conf. This is a place, it's like many hundreds lines of code of variables we set by default. So it's also like a piece of documentation, actually, if you want to know how to configure certain scripts. Some variables are not described in manual pages. You have to look at that defaults file. And if you have a very specific deployment and you want to modify those defaults, you may consider using the vendor.conf file. You know, it's like a middle ground before the defaults and the rc.conf for you to use. Historically, we also support rc.conf local that gets loaded after rc.conf. You may use it for things, you know, maybe you're going to find like a use case for that, but it's not very popular to use it. And then we have service-specific configuration files. So if you want to keep, I don't know, like SSHD configuration in one specific file, then you could do it with the rc.conf.d directory. And you can use like either the etc one or the one in the user local. And the recommended way of modifying those configuration files is with sysrc. It's a pretty smart tool. It understands the shell syntax, so it does the right thing when analyzing it. So you can use it to ask for the current value of your enable variable or set it to something like from yes to yes in this example. The nicest thing is probably that it understands lists. So let's take a look at this cloned interfaces example. In green, we append gif0 to it. So now cloned interfaces list contains gif0. But you can also, and in the fourth example, we see that, okay, so now let's add lo1 and gif0 again. And sysrc understands that first, we have a duplicate, so it removes it from the list, and it also sorts the list. So now you have a very nice maintainable rc.conf file. And you can also remove variables with -x. There are many other options available there. This is like the overview to get you started. And my favorite hack is that rc.conf is just sh, so you can run commands inside. So for example, when you have a LAC interface on your laptop and you like switching from the internet, the wired connection and the wireless connection, you have to have the same MAC address from what I understand. So either you copy the MAC address and put it directly into your configuration file, or you do this horrible thing and you parse out the MAC address from ifconfig every time someone parses the rc.conf. It probably has some overhead. It's probably not the most elegant. sysrc may trip on that one if you ask it to modify, the _mac, for example. But in general, you've got options, and it may be a nice thing to, use if you need it. That's another hack I use. So sometimes I have multiple network configurations in my rc.conf. So I have a case statement there. And what I do is that I just have different numbers for different configurations. Whenever I'm feeling like changing it, I just change the number in the case, right? So it's a very elaborate comment. It just, instead of commenting out a whole block of variables, you can just change one number, like from 0 to 1, and you end up with a different configuration. It's a handy way of writing less. Writing scripts. So, if you want to write scripts, you have to take a look at RC subroutines. And this file is not too long, so you can, get a handle of it pretty quickly. The problem is that it's in the manual page, they mix up functionalities targeted at developers and operators. And so, to put it differently, some of the variables and functions described there are meant to be used when you implement a service file, whereas many others are meant to be used by the operators inside rc.conf, right? So the developer should support setting those variables, but they should be set by the operators. It's a way to override certain things, or maybe, add some extra security. Like, for example, if you want to run SSHD with a different binary, you don't have to, replace the actual binary or patch the service file itself. You can just add SSHD program to your rc.conf, and the service file will know that, hey, okay, so someone provided an override for the binary, so I'm going to use the override. When you run rc command, specifically the start, restart, and reload commands, there are 4 things happening essentially in the background. It's like 600 lines of code, but essentially it's 4 things. There is a setup phase, pre-start, start, and post-start. What's important here is that you don't have to put everything into the start command. You can split it into 3 and keep it clean, right? So instead of always redefining the start, you can let the RC framework handle the start and just define the pre-start command, you know. The closer you stay to the framework, the easier it is to move from a version to version in the future. So regarding those fancy steps you can add to your RC scripts, here are the recent additions. So we have off command. It's a very funny one. So this is the command that we run when a service is disabled. So it feels very unnatural to run anything when the service is disabled, but it turns out it has use cases like when devd is disabled, we also disable it in the kernel so that we don't use memory in the kernel. It's a fairly nice thing. And then for the setup, which is also a fairly new thing. So in the past, we only had pre-start to do all like prepare all the configuration files for a service and maybe like do some checking if like directories are there or not. Nowadays, we have also a separate setup step. It works slightly different than pre-start. You should refer to documentation to understand like the subtleties. But it's a nice thing, you know, and it's a recent addition. It helped. I think it was someone from Open. I don't know, Firewall, one of the firewalls. Yeah, so useful stuff. And now, let's talk about Open Connect. So this is an example of a service script that I called, where I use the multi-instance pattern. So I have just one service script, you know, but I start multiple services. So in this case, I start a VPN for like my VPN, home VPN, work VPN, but it's all handled by just one service script, or like 2 actually. But no, I don't have a service script, you know, for every VPN I have. So now that's how we configure it, you know. So every VPN I use has a different variable, you know, for enabling it, for the username, the server I'm connecting to. I can provide this, you know, the password maybe to get it saved somewhere there on the file system. And I can also like then specify that I want it to be considered a service of my Open Connect. So let's take a look how it's implemented, right? So that's how it looks like. That's a lot. So let's go step by step. The orange one is the very beginning of the script. This is where we handle the second argument, right? So when we say Open Connect start, that's the first argument, and then my VPN, that's the second argument, this is where we start making another instance of this whole thing. So from now on, the underscore service represents our like VPN configuration. And as you can see, the name, it's parameterized with the service name. The RC var is parameterized, you know, again with my VPN. And that happens for every single thing in this configuration file, in this service script. So as a result, I have one service script driving multiple instances of the Open Connect VPN. Right. Sometimes you have to use eval to create those parameterized variables. It's in blue. That's how we can do it. It looks ugly, almost unmaintainable. But once you write, it's write only, right? You don't have to read it. Once it works, it's perfect. In green, this is where we start the actual daemon, and we'll talk about it a bit later when I explain the daemon pattern. But for now, let's stick with Open Connect a bit more. So what we saw was the rc.d Open Connect, but this one is Open Connect services. This one is responsible for actually starting those Open Connect VPNs when I boot my machine. So it doesn't even have a start command. What it does is when RC framework executes it, it just looks for all the Open Connect services in the blue variable and then just starts them or stops them depending on whether it's booting time or shutdown. So it's very simple, but it allows me, you know, to start things early on, and then have this multi-instance pattern applied. So now the daemon pattern. So this is also something that is very popular in RC scripts. Some programs are not easily demonized, you know. They do, like, they don't go into background, or they actually go into background, you don't want it. They don't write a PID file in a reliable way. Maybe they write like weird places regarding their log files. So the daemon 8 command allows you to contain that and have a sensible interface to demonizing your services. So what happens in this case? We have the PID file, which is very important. In yellow, we provide the process name of the actual binary that we want to run with the daemon. And then the command is actually the user has been daemon. So now what we do, with the pink flags, we tell it to save the logs in a very specific place. We tell it to save the PID file of the child, which is the open connect in this case, in this PID file. And then we start the open connect. So what happens now is that we don't really, when we run git status, we have the PID file, right? Because daemon made sure that the child has a PID file, and we can check the status of open connect. You know, we can stop it. We can see the log. It's very consistent. So if you're dealing with a program that is not a natural service, you can use the daemon command to make it a service. And then with the daemon command, you can also restart scripts automatically, right? So if your service, you know, stops, it's like it gets like an error of some sort, then you can use the daemon command to restart it, like after 5 seconds, for example. That's what we do in the orange highlight over there. However, it gets tricky very fast, because now, you know, if something kills your service, you are very happy to get it restarted after 5 seconds. What if you kill your service and then it comes back again after 5 seconds? That's not exactly what we want, right? But this is what is going to happen. So once you start using those auto restart flags with daemon, you have to think very carefully how you implement the stop commands, right? Because when you stop, you actually want to kill the supervisor, the daemon, so that it, you know, also cleans the child, and this way, you know, the commands actually do what you want them to do. So there are examples of it. If you ever need like directions on how to write those scripts, just look for examples in the port tree or the base system. But it's good to know that you have those ways of implementing things. So now let's talk about debugging scripts. So the easiest way, since all of those things are shell scripts, we can use the old sh-x and just print everything that happens in our scripts to the screen, and then analyze this long log, you know, of chaos. It's fairly usable, you know. You can see everything that happens, but it has its drawbacks. First of all, you see everything. For example, like you see sh parsing the whole rc.subroutine library, and that's a lot. And also, as you can see in green, when you have, you know, a test and you check if like some variable is set or not, you don't see the variable name. You just see that the value was empty. So sometimes you have to figure out where you are in the script based on the context of the log lines, because like based on the, like you don't see the variable name when it's tested or passed to a program. So it has drawbacks, but it's the easiest way to do. Another thing that is a bit more standardized is the RC debug variable. You can either set it in rc.conf or just provide it via the environment. And when you do it, your RC scripts start to print out debug messages. So hopefully the developers added some logging, you know, to the services for those situations, and then maybe you can, you know, figure out what is going on. It's an option. it's also something you can use for your own scripts, add those like little debug logs and then enable RC debug when you need it. Most recently though, this is probably something that most of you haven't heard of, we have debug.sh in FreeBSD. This is like a kind of a framework, like a subsystem of the RC subsystem that includes features like enabling set-x selectively to certain scripts or dropping into interactive shell with some nodes around it. It's like a, whenever you were like, you weren't getting like what you needed from set-x and you actually had to modify all the RC scripts that you had problems with. You had to add like manual log, messages, maybe like print the date to know what's happening. Now you have a standardized way of doing it. So hopefully it's going to make debugging easier. Supposedly it's in use for 30 years now, but it was just recently contributed to FreeBSD. So I guess it's very stable and it's been useful. So now we can use it because it's upstream. And now optimizing performance. So it turns out you can trace scripts. It's amazing. So first you have to enable it. It's included in the kernel by default. So you just need to turn on one variable in loader.conf, so before everything boots, right? Then you can reboot, let boot trace4 collect all the logs, and then you can print them out to your terminal. And that's how it looks like. So you see everything that happens from some point in the booting process, all the way through RC scripts, ending with the moment you hit multi-user, like ready or whatever. And then you see a breakdown, of how many milliseconds you spent in certain scripts. I guess you can also see I/O on the right side. I don't exactly remember, but it's a very useful thing. Yeah, it's there to be used. It's built into FreeBSD by default. You just have to turn the tunable on, and you'll be able to access it. It probably adds some overhead, but it's meant to be used when you are developing things, speeding things up, optimizing, and not all the time in production. That's what I think, at least. Testing. Okay, thank you. For testing, we actually have RC tests in the FreeBSD test suite. There are not too many of them, 2 actually. But when I was adding new features like fixing bugs in the RC framework, I had this problem that the reviewers were very resistant to changing the framework, because very often, like, the RC framework is fairly simple. It's not too many lines of code, but it's very dense. Like, there's a lot of things happening in every line of code. So when you change one thing, you may be breaking a different one. So it's there in the source tree, You can check it out. Maybe think of your own test that you would like to contribute. And I think it's a great way to contribute to FreeBSD, because you don't really need to be very proficient with C or like be too annoyed with a certain subsystem. It's, shell scripts with, testing functionalities you probably use every day. So you probably have interesting cases of how to test the RC framework. So yeah, if you ever come up with some patches, let me know. I would be happy to review them. And now some security news. So we have a very interesting new functionality in FreeBSD. It's called the jailed services. And it's pretty nice. So it turns out that some of the services, they don't really need to run on the host. They can be jailed, And we have this magical functionality now where you don't really have to start our own jail, with the whole user space, where we, have to maintain like a separate installation of FreeBSD. We just say that, hey, so, please let this service start in a jail. It's just like a way of limiting what this service can do, but it's still running in the same file system, right? We just jail it, removing some functionalities from it. and you'd control it with rc.conf. So for example, I mean, jailing SHD doesn't make any sense from what I remember, but you can use it for other things. Like inetd, for example, if you want to serve your files from, like, if you want to host inetd in a jail, you can probably do it, and then it doesn't have all the privileges to do like horrible things if it gets compromised. Right, so nice stuff. So in summary, today we learned that RC ecosystem is made of many replaceable parts. So it's very easy to hack on, you know. You can hook into different parts of the framework. You can find ways to implement what you need to solve your problems. And it's very welcoming towards those custom solutions, you know. And there are some common patterns to how service scripts are implemented. We spoke about 4 of them. These are the 4 I identified in my experience with the RC scripts. So one-off pattern, simple service, multi-instance, and a daemon. And the recent developments brought improvements in performance, debugging experience, security, and customizability. That's it. Thank you very much for listening. Yeah, if you have any questions, I still have 6 minutes, so I'm happy to answer them. So the question is if this they will be available on papers freebsd.org.
Why did you use eval instead of setvar to assign the multi-instance service?
Yes, that's a great question. So eval, you know, it's like a shell construct built in whatever. And then setvar is like a special function wrapper we have in the RC subroutines that allows us to, you know, say setvar, the name of this like new variable, and then the value. It's like an eval, it's just hidden. The thing is that from what I read in the commit messages, setvar is deprecated and we are not supposed to use it. Like from what I saw in the commit logs, many years ago, like 20 or something, there was a lot of effort put into removing every setvar. So I guess that's why. That was the reason.
Anyone else? Going once, going twice? Thank you to our wonderful speaker.
You.
Test,
Albert,
test.
is the audio working? Yeah. Because we are not hearing anything.
Okay. You're hearing me? No, not really?
The stream mic works.
Okay,
Can I take this one?
yes.
Is this for here? Oh, it's muted.
Okay.
Mute, where's, oh,
Test, 1, 2.
yes.
Okay, perfect. Yes. Okay, welcome to this talk on Raven ports. After the little technical difficulties, we can start now. Who am I? Just a very quick introduction. My name is Michael Reim. I'm a professional sysadmin. I've been a Linux user for a very long time and then switched camp to BSD, and I couldn't be happier. And I got involved with Raven ports in 2017. So what are we going to cover today? First, I'll start with the background story, because when you're starting a new port system, you of course have to explain why. Then I'm going to introduce you to what Raven ports actually is, so the characteristics and which platforms we currently run on. Then a little bit more about the Raven ports project, in this case on 2 operating systems that I picked for this, and then we're going to do a quick comparison to package source. And after that, I'm going to tell you what the state of the system currently is. And then, that could be the main part, but it isn't. I'm showing you how to use Raven ports. We're going to do the very simple bootstrapping, and then I'll have a flagitiously short introduction to package management. I would have liked to call that basics or at least essentials, but I'm already running out of time. And then we'll have a conclusion. So, ports are one of the iconic innovations of BSD. I guess we all agree to that. And they were invented by Jordan Hubbard in 1993 for the very first release of FreeBSD. And now I'd like to ask the audience who to some degree is familiar with the various port systems. So FreeBSD ports, please indicate. Okay. OpenBSD ports. Couple. Package source. D ports, anyone? Okay. M ports. Okay, thank you. So the background story is, I'm not going to start with Adam and Eve, but almost. In 2003, Matthew Dillon forked FreeBSD 4.8, and the new system initially continued to use ports. This, however, became an issue when FreeBSD started phasing out support for 4.x, because that was what Dragonfly chose to remain closer to on a technical base. The solution that they found was when Jörg Sonnenberger finished porting of package source to Dragonfly, and with version 1.4 they officially adopted package source as their main port system. Package source, the project, recognized Dragonfly as a first-class citizen, but there of course still was a lot of breakage, because in the end of the day, package source is NetBSD's native system. They are all about portability, and they are being nice guys, so they let other people use it too. But of course, they cannot wait for everybody else, and they have to move on with newer versions, and other systems are expected to keep up with that. The Dragonfly people made a couple of suggestions on how to maybe improve this, but that didn't fit in the, into the architecture of package source, at least back then. And eventually, Dragonfly had to realize that they had too little manpower to make this a feasible option in the long term, always collecting the fallout and everything. So they looked for other options. John Marino, who was one of the most active porters at the time, proposed another system. He created what he called Delta ports, which is basically an overlay over the FreeBSD ports collection. And together they form what is called D ports or Dragonfly ports. That one was pretty successful, and the Dragonfly people loved it, especially as it brought many, many more ports to the system because of FreeBSD's much larger ports collection. So in 2013, they switched over to using D ports and have used it ever since. John Marino also started another project, which is called Synth. It's an alternative ports builder. Maybe some of the FreeBSD people know it. It's still available. You can use it. It's an alternative to Poudre. And on Dragonfly, it's basically the only option that you have. But John likes Ada, so he has written it all in Ada. And in 2020, Matthew Dillon ported it over to C, so that it could be added to the base system of Dragonfly BSD as dsynth. And that's kind of how I got involved. When synth was announced, John was featured on BSD Now, and I learned about it there. At that time, I was on the Ghost BSD team. Eric, Andrea, and I decided that we would like to go forward tracking FreeBSD stable instead of dash release. And so we had to roll our own packages, and we picked synth. And yeah, that's how I got involved there. There was another interesting project which I would like to point out quickly. It's called Package Source Synth. John basically brought over FreeBSD's PKG, or PKG-NG at the time, over to NetBSD and several platforms. And he has hooked up package source with it so that the slightly modified synth builder could use that. There was a lack of interest, so a couple of years later he stopped synchronizing with package source, but that was once available. In 2017, a major change happened. FreeBSD ports introduced flavors. John updated synth so that it could cope with that, but this new change broke the one-to-one relation of port and package, and John became convinced that this would be a problem in the long run, increasing the maintenance burden again. So after a long planning phase, he had been thinking about various ideas and whatever. He actually started the Raven Ports project in 2017. So what is it? Some of the goals and characteristics of it is, well, in short, Raven Ports is a modern cross-platform packaging system for Unix-like systems. And what distinguishes us from other systems is, for example, you don't find user-facing make files. They are still used in the background because it turns out Make is quite good at these kind of things. But we have build sheets. They are a bit nicer to look at. And as a matter of fact, you of course cannot just do make dash capital C user ports whatever, or Raven ports whatever. That doesn't work. You have to use the ports builder that comes with the system. We aim for very clean builds. These are build jails, and it's not FreeBSD jails, it's chroot jails. So they're available on all the supported systems. And at some point, I think 2 or 3 years ago, we decided to disconnect from the net after the fetch phase. We found a lot of not so well-behaved software which tried to, in an uncontrolled way, load stuff from the net. And we had to patch that stuff out, of course. We have had variants and subpackages from day one, so they are very well widely used throughout the system. Variants are basically flavors. And for the subpackages, also a couple of years ago, we started what was called the dev split. We introduced dev subpackages, which basically include, or they contain files that you normally don't want on your system, except for when building stuff. So it's static libraries, it's package conf files, and so on. We allow for concurrent installation of multiple software versions like PHP, as you have with other ports trees as well, but we can also do that for TLS libraries. So there is no reason not to install both LibreSSL and OpenSSL on the same machine, and you don't cut yourself out from software depending on one or the other, which is quite nice. We use a custom prefix by default. It is /Raven, and so the system can be used as a secondary package management facility, and it's actually being used like that by most people. We aim for high performance and a highly automated, maintenance-friendly system. And what I would like to point out is we do not have ports owners. We call them contacts, and there is a difference because when you submit a new port, you become a contact. This means other people can, when they have the time for it and feel like it, can update that port as long as it's a minor thing. So we do not have a maintainer timeout or anything. But when there is a major change coming up, you're supposed to contact the contact first. Currently, we support only AMD64 platforms, and RavenPorts runs on Dragonfly BSD, on FreeBSD. Yes, we have Linux support, at least some, but that's limited to glibc at this point. No muzzle, no diodlibc, no mucilibc, what have you. We also support Midnight BSD and NetBSD. And at some point, we used to support macOS. And we used to support for a longer time Solaris. That one went away when GCC stopped supporting Solaris 10, and we deliberately chose Solaris 10 so that packages were upward compatible with Illumos. We have support planned for OpenBSD, and we eventually want to bring it to Illumos again, but no guarantees when. Okay, so the RavenPorts project. The OpenBSD case is interesting. Why have we not done the platform bring up yet? There is a blocker. RavenPorts is designed in a manner that it makes heavy use of null mounts. When OpenBSD forked from NetBSD, they inherited them. But in 2005, they removed them. I found some commit messages and discussions where people said, eventually we'll replace it with something better. But as of my knowledge, this has unfortunately not happened. Most of the OpenBSD people seem to work around these issues using local NFS. We could probably do that, but that's certainly a lot of work teaching our whole infrastructure and build system to use NFS, and that simply has not happened yet. Another interesting thing may be the collaboration with Midnight BSD. It is the latest addition to our platforms so far. It was done in spring a year ago. I had some mail contact with Lucas Holt, and he even added the bootstrapping option to the first boot script. So when you're installing a recently new Midnight BSD, on the first boot you get asked, do you want to bootstrap RavenPorts? The main benefit for this small project is that we make more and newer packages available to them. There supposedly has been some positive user feedback. Most people seem to like that we have recent versions of Firefox, while Midnight BSD by default doesn't have that. There are other examples, for example, LibreOffice or the whole TechLife distribution and things like that. And another good thing about that is when building packages on Midnight BSD, when having TempFS disabled, there is a problem. A bug is triggered, we have yet to investigate, but platform diversity is interesting and is helpful. I wanted to point that out. So a quick comparison to package source, because, well, we're both portable, so it kind of suggests itself, but I'm going to spoiler here. Except for the portability side, we have pretty different goals actually, so package source and Raven ports are by no means rivals. We totally lose the portability contest if there is any. Package source is implemented in very common languages, while Raven ports uses Adder. Package source supports, I think, 20 different platforms. We're far from that, we only have 5. And they can do that across 15 different CPU architectures, and we have 1 at this point. Also, it's the much more established and older project. They have, I think, about 20,000 ports, or slightly more, while we have about 5,400. And when it comes to maintainers, it's kind of the same. Package source, according to Repology, has 415, while we have 16, which is actually too much, but this is because how Repology counts things. So in the numbers game, we'd also lose. When it comes to other features, one that I really like about package source is they have reliable quarterly releases. We don't have that. We have infrequent releases, basically when there is time. But Raven ports can be useful for a number of reasons. For example, package source does not have binary packages for most of the platforms that they support, while we actually build package sets for all these platforms, more or less regularly. So on the package source side, systems other than NetBSD are basically best effort, while we regularly test things. Package source is more on the traditional side of tooling, because when you run on very old hardware, that's all you can do. While Raven ports, on the other hand, focuses on more modern tooling. So package source prioritizes portability, while we prioritize concurrency and automation. Also, due to the much larger repository on package source, the freshness, according to Repology, is usually below 70%, while for Raven ports it's usually above 95%. We have been the long-standing champion in that category on Repology for a couple of years, but I think 1 or 2 years ago other projects started catching up, which is good. So, is it ready for prime time? That totally depends on what you want to do with it. It has been in development for more than 7 years now, but we've kept a bit of a low profile because we were mostly working on it before we wanted to present it to the world. So you can expect that it's not going to silently go away tomorrow. The statistics also probably say that it's kind of healthy, even though most of the contributors are one-time drive-by contributions, I will admit that. So we have a relatively low package count. If you find that what you're interested in is there, it can be helpful. But packages are very lightly tested. And that is due to the very small user base that we have until now. And that one is important. So far, we've been using a fork of FreeBSD's PKG called Raven SW. It was slightly modified, so a pretty familiar package manager for most of you. But we finally finished our own package manager, which is better tailored to our use case. And right now, the transition is in progress. You can already use it on Dragonfly and FreeBSD. It has been bootstrapped to NetBSD and Midnight, but we're doing a conversion of the package name scheme. You might want to wait a couple of weeks for the dust to settle there, but otherwise it should work. So basically, it is ready for early adopters. If you're feeling courageous or adventurous or whatever, you can do it now. Okay, so how does this work? How do you get it on your system? We have a pretty convenient downloader script, which will bootstrap it. So you can fetch or FTP on other systems it. And of course, you'll then read it because you don't execute code you get over the net. You can also do manual bootstrap. There is instructions for that, but that's the convenient version. I would like to point out the highlighted in new here. That's currently during the transition, but that will go away and you will just be able to use the usual downloader when we complete that. It downloads a static binary and then uses that to install the proper packages there. As you can see, it downloads 3 things. That's because of the subpackages. There is the man subpackage, the primary subpackage, and the set subpackage. The set subpackage is special in meaning all the subpackages. You can use that as a shortcut to install basically the full thing, whatever it is. And when it finishes, there is this little message that you can start installing packages with it now, and that actually works. What you need to know to use it is how the package naming works, and that one is a bit special. We basically have 4 fields there, and they are separated by tildes. The first one is the namebase. That's basically the name of the upstream project. Unless they are doing something fancy, then we are normalizing the name a little. The second field is the subpackage. We already talked about that a little. And the third one is for the variant. By default, it's the standard variant. Every port has that. And there may be additional ones, but we'll get to that in a second. Yes, and then there is, of course, the version there. And for namebase, that one can have a prefix, which is used for interpreted languages like Perl, Python, Lua, PHP, whatever. What does it look like? Basically, in the upper box, you can see listing the installed packages. These 3 are what will be on your system after just the bootstrap, so it's pretty much just the package manager itself. And it provides the default features that you would expect. You can search, for example, for Firefox. You can also do -E for an exact match. I did that for Vim because otherwise I'd also find NeoVim and I think VimB and things like that. In the example in the bottom one, you can see there's, for example, 2 man packages. That's because one is standard variant and the other is the loaded variant. The loaded variant in this case is configured with other build time dependencies. It usually has additional dependencies and that it draws in, so the other one is lighter. You can install packages basically just like that. If you want ZSH, you can rvn install ZSH, and that will do exactly that. It will pull in 10 packages in this case, and you can see 4 of them are for ZSH, including the docs, the man pages, basically everything. If you want less than that, you can do this rvn install ZSH ~p. And I've just shortened it. You could also spell it out. So ZSH ~primary ~standard, but you don't have to. As soon as it's unambiguous, you can use it. And you can see in this case, it's just 7 packages because we left out the man pages and the docs here. If we try to do the same thing for Nginx, we get an error. And this is what it here says. Multiple variants were selected because Nginx also has a standard variant and a loaded variant. And you cannot install variants concurrently because, for example, there is the Nginx binary in both of them, and you would have a clash in the file system. So to disambiguate that one, I need to indicate Nginx tilde primary tilde s. That's the shortest one. And then we'll come to the conclusion. There is, of course, a lot of future work that needs to be done. Right now, the documentation is a little bit scattered throughout various sources. I'm working on a proper handbook. Actually, I have a first draft of it available, but it still covers the old package manager, so it's not ready for release. I have to redo that. We definitely want to add many more ports. There is a wish list available on GitHub, and people interested are free to request ports there. John has been working on a vulnerability DB, so the RVN audit command will probably pop up in the nearest future. And as you can see, the other things are, well, things that we would like to do, but I put a question mark there because I have no idea when it will happen or even if. We would definitely like to support OpenBSD, but for that we have to revisit NFS. We would like to add more CPU architectures. We have actually a server-grade ARM machine running FreeBSD, but the bootstrap has not been done yet. We want to support Illumos, and we want to find a more predictable schedule for new package sets, and ideally some kind of CI. So in summary, Ravenports is a cross-platform packaging system which tries to use a clean approach, like, for example, some of the Linux systems which also have the dev or devel subpackages where they split out stuff. We're officially supported as a secondary system on Midnight BSD. And right now, we're talking to the Dragonfly guys because they might want to switch package systems again in the nearish future, as I'd like to say. It's the typical open source story. There is no guarantees whatsoever. This is a project done by a couple of people in their free time. You're free to use it while claiming all of the responsibility if something should break. Any kind of feedback and contributions are very welcome. And if we still have time, yes, I can take it. Yeah, I don't know if there's a mic anywhere. Yes, there is.
So I really like the idea of the offline builds. Sorry for my voice. But how do you handle stuff like NPM and Maven, where it continuously wants to get stuff from the internet?
That's a bit of an headache. We don't have Maven, fortunately. But with NPM, yeah, we have to collect the fallout basically with every new version. We do that. So it's testing and finding out what we need to get into our manifests and stuff like that.
So, question. Obviously, the hardest part from starting from changing the packaging system is like you have all this pre-existing work. How did you do anything to make it easier for not to lose all your current packages? Any tricks?
You mean the system packages, or?
No, when you made Ravenports, then did you lose all your existing prior packages?
No, it installs to an alternative prefix. So whatever you have by other sources stays untouched. You basically add other packages on top of that.
No, in the sense of like you lose all the prior work that was done by maintainers.
Okay. No, I don't think so, because you can combine systems, and actually most people do that. For example, on Midnight BSD, they use their native imports for most of the stuff, and combine that with some things from Ravenports. And I did that on NetBSD too, because there are a couple of things that are not in package source, and we have that, but most things are in package source, and we don't have that.
So you said earlier that one of the catalysts for starting the Ravenports project was the introduction of flavors into FreeBSD ports. But then later you said that you have your own kind of flavors. Why is flavors at the same time something that was such a problem that you built your own package subsystem, but then you adopted it yourself?
That's a good question. And I think this is because the design decisions that John made when he built dports, he assumed that there would be this one-to-one relationship. And when FreeBSD ports changed, that was basically no longer the case. And he said, okay, we will drown in additional work again. I don't know the technical reasons for that, but that is basically what has happened. They have used dports for many years now, and just pretty recently, the people whom he handed it over to have said, okay, this is too much work, and we need to get out of that.
Okay, that sounds reasonable. Thank you.
No more questions?
Okay, if there are no more questions,
okay.
I would have liked to show you with my other laptop, which, however, we tested it yesterday. It worked. We had the display working, everything, and now I couldn't get it to work. It simply didn't find it.
No.
It's running on Ravenports almost exclusively, almost because I need the KRM DMOD packages from FreeBSD for the graphics card to work, but the rest, the whole graphics stack is from Ravenports. The tech toolchain that I built the slides with was from Ravenports, and even Ocular, the PDF viewer, was also from Ravenports. This is not true on this system. This is basically just a common FreeBSD. But yeah.
Yeah, unfortunately, HDMI is still black magic. Well, thank you very much for your speech, and give him a round of applause, please.
Thank you for attending, and if you have any further questions or you want to reach out, these are the addresses.
Why is Linux in your email address?
Thank you. For historical reasons. Maybe that. No, it's actually, I registered that domain in 2012, slightly 1 year before I switched camps. Sorry.
Okay, thanks.
And start. Here you go.
Okay. Thank you very much. Okay, so today I'm going to talk about end system multi-homing. Microphone's not on. Any luck now? Just the slide. One, two, 1, 2. Yeah. All good. 1, 2.
Oh, I can borrow this one.
All good. 1, 2. Okay, that's better. Now I can hear myself as well.
Secret news.
Okay, take 2. Today I'm going to be talking about end system multi-homing. So I'm going to start off by explaining what that is and why it's useful. And then I'm going to get into ILMP, which is the specific solution that I've been looking at recently. I'm going to give some details of how we've implemented this in FreeBSD. And then I'm going to finish up with some data from some over-the-internet tests we did between St. Andrews, where I'm usually based, and one of the IETF meetings. This shows this solution working over the public internet. But to start off with, why do we need multi-homing? What is this problem that we're trying to solve? This is a kind of once upon a time picture of how we might think about the internet working. And if we ignore mobile devices and wireless and a couple of server deployments, this is still how we might think normal setups work. So we have our endpoint. It is connected to our network at one point. So it's a node that has one identity. We think of it as being one unit that does a particular task for us. And it has one location on our network. And so we give it one address. And that address tells us where it is and also who it is. If we want to communicate with someone else, we need their address. So that would tell us who this other endpoint is and where they are. And we send data out. It can find any route across our network to get there. We don't care about the route. We just use the addresses to find the endpoint. So in this example, we could send data out to our ISP, and it could then go straight to ISP B and across here, or to ISP C and take a sort of indirect route and eventually get there and still get across. The problem starts to appear when we get to deployments like this. So now endpoint 2 has 2 points of connectivity. So it still has one identity. It's still one endpoint. Maybe it's one server doing one task for us. But it's got multiple locations. And there's various reasons we might want to do this. So it could be for resilience. We want to keep operating even if our ISP goes down. It could be for throughput. We want to make use of multiple links at once. Or it could be related to mobility. So maybe we're moving between different networks and we want to maintain connections across that. So regardless, we have multiple locations, and it's now unclear what should happen to our address. So if we're following the logic from before, this should maybe be, it should maybe have an address of B2, or it should maybe have an address of C2, but it's unclear how we would combine those. So I've used a kind of IPv6-like notation. If these were IPv6 addresses, then the B part and the C part would be routing prefixes. They occupy the same bytes of the address, and we can't just amalgamate them. So the problem we have is that the semantics of an address are overloaded. It says both an identity and a location. And so those values become sort of entwined. We can't separate them out and manage them as nicely as we might want. So this is where we get our multi-homing problem. If we have multiple locations, we can't reconcile it into one address. This is related to the problem of mobility. So if we're moving between different networks and our address is changing over time, we might go from having one location to having one location still, but it's a different location than we used to have. So mobility is a kind of special case of this where we do the multi-homing dynamically. We substitute in different addresses. I'm not going to look too much at multi-homing today. I'm just flagging it here because it's relevant at a couple of points. there are a handful of ways we could try and solve this. So we could use multiple addresses. So if we're meant to have either address B2 or C2, maybe we can just use both of them. And whenever we have a transport session, it picks one of those addresses and uses that to create this connection. This means every transport session is forced to use one ISP and one link. We can't change the address mid-session without terminating and restarting, and so we're stuck on one link. So if our ISP fails, and that's one we happen to be using for a particular transport session, that session must terminate and restart. And this is not ideal, especially because there's not really a problem at the network layer. Our endpoints are still both connected to the same internetwork, and data could still get from one to the other. We just have this problem because we can't address things in a way that lets us get around link failure. We also can't do link aggregation, so we can't use both links at once within one transport session. We have to pick one, and if we've got sort of two links that have limited capacity and we want to sort of combine them, we have no way of doing that. And similarly, we can't do dynamic load balancing. So if, for whatever reason, all transport sessions to our endpoint are going through ISP B, we can't force anything onto our other links. We have all this capacity and we have no way of using it. To solve this, we could create a new kind of address. So I've said ZZ2 here. So this is outside of the range from either ISP. So we can now just use one address and say this uniquely identifies us, and if anything is to be directed towards us, it just has to be routed to that address. And then we convince our ISPs to route traffic for that address to us. This lets us keep one transport session to one address, which is nice, and it lets us use both links, so we can get this dynamic load balancing or aggregation or failover. The problem is we're now having to use a provider-independent address, so one that's not in the address range allocated to each ISP. Now, typically, providers will want to aggregate addresses, so rather than saying, I have this list of distinct addresses that I can forward traffic to, they'll use a range. They say, I can forward traffic to everything between this address and this other address. And this is good because it means you can make a very compact routing table. It's just a check if something is in a particular range. When we start introducing provider-independent addresses, they don't fall into this range. We can't aggregate them in the same way. And so now our routing table lookups have to check a range and also this explicit list of provider-independent addresses. So we fragment the address space, and these lookups become a lot more expensive. And so if every time we do a routing decision, we have to do this costly lookup, that's not good for the entirety of the internet, even if it fixes our one problem here. We also might have an extra financial cost. So now, in addition to having to have two ISPs and get links to both of them, I have the extra cost of getting this other address that I work in. So this is another approach that uses addresses in a way we kind of know how it should work, but it's got its own set of problems. We could go and try and fix this with applications. So if you've looked at Quick or multipath TCP, this is what they do. They say, the approach where we use multiple addresses for one machine is just about usable, right? It works. We just need to use a specific address for a specific link. So maybe we can make applications manage that for us. We need some kind of extended API here to pass that information around so that the application can know it has multiple addresses to use and can sort of inject that information in and switch between things. But this potentially gets around this problem. Assuming we can find application protocols that we can build the applications that do this, we can define this API, and then we can deploy it to every single application that's ever been created. So things like Quick work quite well if you're Google. You've got a big team of developers, and you just need to fix Chrome and servers, and then most of what you worry about works. If you've got a smaller group of developers, then it's a much bigger ask to suddenly learn a new protocol stack and redesign your system to use that. This is also a kind of protocol NIMBYism in that we've not actually solved the problem. We've just said, maybe someone else can solve this problem for us. So if we could find a way to solve this problem at the network layer, that might work better. It lets us keep using UDP and TCP without having to rewrite all our applications. One last approach that I'm not taking here is to use middle boxes. So there's a whole host of attempted solutions like this that do some kind of middle box at the border of your network that manages the multipath protocol. This means you don't need to do anything to your endpoints. They can still act like they're single-homed. You don't need to do anything to your ISPs. They can still act like they're just forwarding traffic to a single address. We hide the complexity in our middle box. The problem with this is that hiding complexity introduces new problems. So particularly with something like mobility, if I'm using your network and it's behind a middle box, then I might have a particular idea about what my connections to the internet looks like. That means I can handle the step onto a different network if I'm moving onto a different Wi-Fi network or switching onto 5G. I might handle that in a particular way because I think I know how my connection works. But it turns out because of your middle box, I actually don't. And so that then falls apart. So we're introducing new complexity that we can't see or control, and it might break future innovations or lock us into mindsets that sort of prevent us from bringing in new innovations. So instead, a solution that we might want to look for is something that is in kernel. So we can deploy a fix to our operating system through whatever mechanism we use to update the OS, and then it will work for all applications. We don't need to worry about getting every developer on board. We want to do something that doesn't involve creating a new API. So again, we don't need to change applications. We can just deploy this and it will work kind of out of the box. If an application uses the updated operating system, everything will fall into place. We want to do this on the end system rather than a middle box so that whatever complexity we introduce, we can see and control and account for in anything else that we do. And we want to reconcile these last 2 points. We want to have multiple provider aggregatable routing prefixes, and we want to have a single transport layer ID. So we can have one transport session that uses these multiple routing prefixes. And this is where ILMP comes in. So this is the Identifier Locator Network Protocol. I've got some links at the end that can point you to the RFCs that define this in detail. I'm just going to give a very quick overview of this so that we can then see how we implemented it. I'm going to contrast this with IPv6. There are ways to do similar stuff with IPv4. My implementation is the IPv6-based one. That's what I'm going to focus on. IPv6 addresses are formed of 2 parts. So you've got a routing prefix, which is the first 64 bits, and an interface ID, which is the second 64 bits. And I've colored them here to say the routing prefix is a network layer value. It identifies uniquely a network. And the interface ID is a kind of link layer value. It uniquely identifies your interface on the local network. And when you combine these, you get a value that uniquely identifies the network you're on and uniquely identifies your device on that network. So it's a unique address for your device on the internet. ILMP slightly changes this. So we use the same syntax, and we keep the same routing prefix, so it means the same thing. It still identifies our network. We're just going to call it a locator or an L64. And instead of using an IID, we're going to use a node identifier or a NID. This is in green the transport layer value, in that we manage it at the transport layer and we propagate it down through the stack. Rather than identifying an interface, it's identifying a node, so we then add it to every interface that we were using, and it gets managed at another layer. To get into a bit more of the semantics of these values, NIDs use the same syntax as IIDs. They can be managed in the same way, so you can integrate them with Slack and Neighbor Discovery Protocol. And we can make them random and ephemeral. So there's work to do similar stuff with IIDs. With NIDs, it becomes a little easier to manage because we can integrate that management with our transport sessions. It identifies a node, so this means no matter which interface we're using, this value will be the same. Even if we then move between networks, our routing prefix might change, but the NID will be constant. So we can use this as the invariance in our transport sessions. It indicates the endpoint. L64s, on the other hand, are excluded from transport state. So although they have the same syntax and semantics as routing prefixes and IPv6, we remove them from transport state. We just ignore them. We don't count them in checksums. We don't use them in PCB lookups. They're not part of the end system state. This means that they are mutable, so we can change them and substitute in a new one, and our transport session can still continue to operate. We just need some way of gluing these together, which means the binding between a NID and an L64 to populate the address fields of an ILMP packet is managed dynamically. So we find whatever NID our transport session is using, and we find whatever L64s happen to be available to us, and then we join them together when we send packets out. We also need a little bit more signaling. This is more important when we get to mobility, where we want to dynamically change the set of available locators. But we can use it for multi-homing as well, which are locator updates. These are new ICMP messages. We've got the IANA code points for them. And these let us update data structures within the kernel that we use for this dynamic binding. So this means that if the set of locators that I am using for my endpoint change, I can send a message out to any endpoints I'm communicating with and say, stop using these locators and use these new ones instead. Or even just, you can keep using this locator, but also add these other ones to the set that's available. I can sort of announce my presence on these extra links. And because we can do all this within the kernel, we can do it without having to change the API. So applications don't need to worry about anything. So onto some of the implementation details. So I did this work in FreeBSD. I did it as part of a PhD. This was my first exposure to FreeBSD, which meant that the first time I ran a BSD system was one I'd compiled myself, which was possibly not the most sensible way to approach this problem, but it was certainly a way of learning a lot. The general idea of what we've tried to do is keep all the dynamic bindings in a new data structure. We called it the ILCC. This used to stand for Identifier Locator Communication Cache, but that's a misleading name because it's not actually a cache, so now it's just the ILCC. It doesn't stand for anything. Whenever we send anything out with TCP or UDP, they consult this data structure to get the latest dynamic binding, use that to create their packets and send them out. And then we can update the ILCC with locator updates to get information about remote nodes, or with router advertisements to get information about the locators available to us locally. So we can sort of split it out into these different modules, and then add them in bit by bit. So to start off with, a bit of a closer look at UDP. This turned out to be very, very easy. So the UDP code was easy enough to make sense of. All you had to do was change the way PCB lookups work when you receive a packet, and which we'll come back to in a moment, and update the PCB with the latest dynamic bindings whenever you try to send a packet. And then when the packet got generated before being sent out, it would use the latest values from that PCB, and so it would use the latest locators. The protocol control blocks are stored in a hash table. Now, normally the hash is a hash of the address. So you receive a packet, you hash the address that it's come from. That gives you a list of sort of candidate protocol control blocks, and you search through that to find an exact match. And you match the local and remote addresses and the local and remote ports. because ILMP excludes the locator values from the end system state, and because they could have changed since we created the protocol control block, we just use NIDs instead of addresses. Which means if we want to do this lookup correctly, we first have to do a hash of the NID instead of the address, but can then use the same data structure. And then when we search through it, we just want to match the NIDs instead of the full addresses. So again, it's a very small change. And we can put this in conditional compilation, so it can just compile away if we don't want it. In order to do this, to know we should do this lookup instead of the IPv6 one, we need a way of identifying ILMP packets. And that's where the nonce header comes in. So we add an extension header, which is, we use the IPv6 extension header framework. We have specific ones defined for ILMP. They include a nonce, which helps with authenticating our locator updates. But the useful bit here is that if we receive a packet and it has this extension header, then we know to use the alternative lookup. This was, again, surprisingly easy. So the extension header code was all there in the PCB. We could just initialize that with the right layout for the ILMP header, and it would automatically get added into every packet we sent. And this was surprising because I tried to look through the kernel to find some other code that used this functionality and couldn't. So I don't know if there was other functionality and it got removed, or if this was just written into the operating system because it's standardized and it just happens to never be used until now. But I am grateful that it works because that saves me a lot of difficulty. And then the last bit we need to sort of glue all of this together is some stuff for session initiation. There's a modification to get address that says if you're getting information about an ILMP node, it has different DNS entries. We just use etc hosts. But this means the get address info call works out that it's looking at an ILMP node. It populates the ILCC with information about the remote node. And then when we try to connect to it, the connection will check if that entry exists, and if it does, it will create an ILMP session instead of IPv6. We set the NIDs explicitly, so we say this node has to have this NID. We have a tool for that. Eventually, it might make sense for that to get integrated into ifconfig, but there are still some details of exactly how those semantics would work that mean we've kept with using a separate tool for that for now. Local L64s are added based on router advertisements. So it's using IPv6. This stuff has to be getting sent out. You pick up these to work out what is available in the network you are on and which router is responsible for forwarding stuff from that prefix. There's a little hidden complexity here in that we also need to track which, we don't just need to track the locators that exist, we need to track which interface they're advertised on and what the next hop router is to make sure that when we send packets out, they go to the router responsible for forwarding stuff from that locator. If we don't do that, there's a risk we try and forward traffic based on just the destination, and it gets sent out by a router we're connected to, but with the locator for the other one. And that's likely to get dropped as a kind of spoofed packets defense. But we can handle all this in the ILCC. We just parse the router advertisements and add that in, and then we specify the next hop when we go to send the packets. When we try and start a new connection, it defaults to trying to use ILMP, assuming it's all enabled, and it will check that it has the information about the remote host, that it has at least one NID that it can use, and that it has at least one local L64 to use. And if all of that is true, it will default to ILMP. Otherwise, it falls back to IPv6. You don't actually need to set NIDs explicitly. So I've got some experimental stuff for maintaining a pool of available ephemeral NIDs. My research is primarily focused around using this as a way of achieving privacy benefits. And this was looking at generating per transport session addresses. So the idea was you create a unique NID, you use it once for one transport session, and then afterwards you deprecate it and discard it before anyone else can use it. This is easier to do with ILMP than IPv6 because we can manage it at the transport session, which means we know when it's in use and when we're done with it. There have been efforts to do similar stuff by modifying interface IDs at the link layer, but that's much trickier because you don't know if it's still in use. And so it's much more costly to try and expire them. And then there's TCP. So all of what I just said works for UDP, and most of it is also what you use for TCP. But TCP is much trickier than UDP. And there's a couple of reasons for that. So although in principle we're doing the same thing, we're using all of these structures and the same way of updating the dynamic bindings, and we just need to do the thing we did with UDP when we send packets and the thing we did with UDP when we receive packets, the code is much fiddlier. So the UDP v4 and the UDP v6 functionality is in two different files. So if you're modifying the UDP v6 stuff, you don't need to worry about any of the v4 stuff. That's not the case for TCP. It's all in the same set of files, so each function will handle both IPv4 and IPv6 packets, which makes it more complex. What makes it even more complex than that is that it's conditionally compilable. So you could compile that without the IPv4 stuff or the IPv6 stuff. And I was trying to add another layer of conditionally compiled codes that would only apply if it had IPv6 support. So there was just a lot of preprocessor commands to try and make sense of. The other big headache was SYN caching. So to prevent certain DDoS attacks, when you receive an initial SYN message to start a TCP connection, you don't create the full protocol control block. You just create a small entry in a SYN cache. And if the TCP handshake is successful, then you create the full protocol control block. This is to stop someone sending a bunch of SYNs to make you generate your big table of protocol control blocks and do all this work only to not actually have any real connections. The problem with this is that I'd already done the UDP approach and everything was engineered around the assumption that I had a protocol control block to work with. Now suddenly I didn't. So I had to go and generalize all my codes to work with some other structure that would refer to it to make it work for both the SYN cache entry and the PCB. But we got there, and this does now work. One last comment to make about this is there's an open question around how we choose which locator to use. So if we've got multiple paths, the question is which one do we use? If one goes down, then obviously we can fail over to the other. We probably want to do kind of even usage between them in some sense to try and load balance. But it's not immediately clear how we do this and how we detect this. So that's an area for future research. The current approach is just to send a packet out on alternating locators. This was, again, a privacy experiment, so it was about disrupting real-time traffic analysis. It introduces some unexpected problems, which we will come back to in a couple of slides. This is also all oblivious to any kind of congestion control approach. So congestion control typically will see loss, will take that as an indication that there is something going wrong on the path between your endpoint and who you're speaking to, and start sending less data to try and deal with that congestion. If you're using multiple paths, then you need to do something different because you now have, even if you just have two locators, two paths, if you have two locators and the other node has two locators, you have 4 different paths, each of which will overlap a bit with some of the others. And so the states you have to manage for path selection and congestion control becomes much more complicated. We've not looked at that in detail yet. So far, we've been trying to check that this is a viable approach and that it works over the public internet. This is the next step. There's also some interesting questions about what you do with retransmissions and ACKs. So if you've lost data, do you retransmit it on the same link that you initially sent it to sort of treat it like a retransmission and it's exactly the same thing happening? Or should you retransmit it on a different link so that you're less likely to hit whatever caused you to lose it? Or is that complexity not worth worrying about and you send it out on whatever link is available? Similarly, do you ACK data on the same link that you receive it? Or do you ACK it on a different link, which then risks it being lost? Do you ACK data from across all links in one message? So there's a lot of stuff that we could explore here. That's questions for the future. We have a working prototype. The code's up on GitHub. There's a QR link to the end in one of the later slides. This is based on FreeBSD 14. We're in talks around trying to get this merged eventually, once we've sorted out the last couple of caveats. It is now stable. It doesn't, we can use it for extended periods. It's probably some of these congestion control issues that might be an issue to wider adoption, but like I said, they're an area for ongoing work, and they don't always matter so much. Going to finish up with some data from a demo. So for this demo, we sent some kit over to an IATF meeting in Vancouver, and we kept a server running back in St. Andrews. So we then did some tests with iPerf. We've got the iPerf server. It's then connected to the global internet. And then at the IATF hackathon, we had an edge router that was again connected to the internet. And our edge router was connected to our client machine. And we had 4 different links here. So it's sort of at the last hop, we've got this multipath functionality. And for the demos, we started off just using one link. And then 20 seconds in, we'd bring another link online, then another, and then another. And then gradually turn them back off again to go back to just using the original link. So this would show us sort of going from just using one link as normal to a sort of full 4-path multipath setup, and then switching back down again. The goal of these experiments was to check for connectivity. So we weren't sure what would happen with extension headers as we sent them over the internet, and also with checksums that didn't include routing prefixes. So the main thing we were measuring is just can we send data from A to B? This was not intended as a performance test, so we don't have baselines for IPv6 to compare this with. That's something we'll want to do in future, but that was not the purpose of this test, which is why we've got that kind of data here. First up, UDP. So we've got throughput plots here for each interface over the full duration of our iPerf run. So as you see, we start off sending everything on one link, and then throughput here drops when we bring our second link online. So we've got some kind of limit that's saying this is the maximum amount our application will send, but it will split it across the available links. And then when we bring the third link online, we've now got a third here, a third here, and a third here. And then when the fourth one comes up, we split to doing quarters on each link. And then as this goes down, we go back to a third on everything. As this goes down, it goes to 50-50, and then back to doing everything on one link. So we get this very even spread of load across all our links, which is nice, right? We are taking full advantage of what's available in that we are not sending everything out on one link and creating more congestion there. We will hopefully be creating less congestion because we're load balancing. And if we aggregate all this up and look at the total throughput, it looks like this. So we're not getting any drops if we have our handover. We can just keep using all 1, 2, 3, or 4 links, and then 3, 2, and 1. And it's not impacting the application, at least in terms of throughput. And then there's TCP. So the alert amongst you will notice something weird happening at 90 seconds. And when I point out this is a log axis, you'll realize this is very, very weird. So we're fine all the way through, everything coming up, and then things start going down, and we're fine for a bit, and then suddenly we get a drop. We get a drop in throughput of an order of magnitude, and take a while to gradually recover until we get to sort of this bit at the end with just one interface. It looks even weirder when we get into the looking at all 4 interfaces. So we start off with this bit. When we've just got one link, the performance we get on that link is the same as the aggregate, as you'd expect. Then when we go to 2 links, we start to get this sort of much spikier pattern, even though we're still getting the same kind of performance in the overall aggregate performance. So sending packets out on alternate links is not quite giving us this sort of smooth dip. It does have bursts on some. It doesn't have bursts to the same degree as MPTCP, if you've looked at data from that. It would use a full congestion window on one path and then switch entirely to another. We've got a bit of a more even pattern for the most part until we get these sudden drops. And this one's happening at 70 seconds, your other's happening earlier. This does not map onto a drop in performance in aggregate. So this is, we stop using one link and switch to using another. And then this one comes on, it drops off at 80 seconds, and then 10 seconds later we start having problems. We are still exploring all of this data, but we were not particularly surprised by this. So what we believe is happening is that we're getting some loss in this handover. So that link goes down, maybe an ACK gets sent to it and is lost because that link is now down. So we detect some loss, we retransmit some stuff, and everything falls apart. Because now our retransmissions are getting spread across 3 interfaces and are arriving out of order. And that the out of order transmission is then getting interpreted as more loss as we get this sort of spiral of everything falling apart. Like I said, this is not surprising. We are not doing anything at all with congestion control to account for the fact that we're using multiple paths. We've just tried this out to see what would happen. If we had multipath aware congestion control and we're selecting the locators appropriately to manage that, then we'd expect this to be smoother and to not have this drop in performance because we would have defined a way to manage it rather than just hoping for the best. So the key takeaways from this are that we can do end system multi-homing. The UDP results show that. We can just switch between interfaces. We can send this across the global internet. So there might be middle boxes on certain enterprise networks that cause us issues, but across the public infrastructure at least, this works, and we can start using it and deploying it. We can do fair multipath, where we utilize all the available links and spread traffic across them. But we've still got some work to now get to with multipath aware congestion control and locator selection. But we can now do that because we have this working solution. There's a QR code there to the code release that also has some links to some papers and some data from a previous set of measurements we did. We'll eventually release the data behind those figures. We're just in the process of dissecting it and writing it up. But I'm going to finish up there and can take any questions.
Are you planning on making this in any way available or visible to the applications? For example, by picking a reserved IPv6 prefix, and then you can sort of like ping a node ID or something?
So the work so far has avoided doing that. So we've very intentionally avoided making anything visible to the application. The idea being that we want it to be deployable as a kind of kernel update. If we did want to do that, we'd probably do it through an expanded kernel API. So if we did define some new functionality, we'd say, sort of, here's a modification to the way you start a connection.
Is there any way to make this work if the network forces a specific host ID on you, for example, using stateful DHCP v6?
Yes. So because NIDs work like IIDs, if we did have something like DHCP to manage them, you could allocate that out and use that as a NID. It would start to give you issues if you were multi-homing across different networks that were both doing that. Because you couldn't use the same NIDs across them then. But if you had a server, say, that was single-homed, or that you had DHCP sort of on both networks, but it was aware of what it was doing, then it would be fine.
Yeah, because middle boxes are always so mindful.
Yes. But a lot of IPv6 stuff is Slack-based anyway, so a lot of the time we can avoid that. Yes.
Hi, I'm just wondering, those results that you saw with the TCP, did you consider that it may have been due to the packets coming in out of order?
Yes. So we think that we're getting this sort of out of order delivery, and that especially once we get to a higher number of paths, we think when you've got a couple of paths, it's low enough that you don't get much. When you go to higher paths, you get this out of order delivery. It's going to get detected as sort of lost packets much more quickly, and we'll get that drop in performance. We were surprised, though, because we were just using 4 links at the edge router. We'd have expected that to be very minimal. So we need to look a bit more closely to see what's going on and maybe do some follow-up experiments at the next IETF.
Yes, it would be interesting to just see what the percentage is on higher speeds then, what that retransmission is.
Yes.
And then just one last question. Did you consider doing the same experiments with something like ESP traffic?
No.
Yeah.
So, one maybe more question, I think. Yeah, like 2 minutes left.
Did you, I wasn't sure if you had to do these updates on both endpoints, so both endpoints need your changes, or just one endpoint does?
So far we've just done them with one endpoint. At least that's what we were doing in these experiments. I have done some smaller tests with doing it on both. So in principle, that's absolutely fine, because they're both using the NID as the endpoint state. You can change either set of locators, and the protocol at least is happy. The slight risk is if we are communicating and we both change networks at the same time and do a hard handoff, and we both send out updates to our old networks, we could both sort of migrate out of our own connection. But as long as you're not both very highly mobile, and if you can sort of manage some kind of soft handover, then that should work.
So, like 1 minute left. But, yeah. So, like more questions or?
Couple more?
More, yeah. 30 seconds left.
Yeah. So I'm wondering how big is the actual diff and the change? How hard do you think would be to integrate it?
So we've got, it's sort of fiddly because it happens in a bunch of places, right? We've got this, so all the dynamic binding stuff is in a new file. So sort of one big file to add. And then there's a bunch of sort of stuff between hash defines for like a hook into that from the root advertisement code, and a hooks into that from sending and receiving UDP, and into that for the TCP code. I can't remember off the top of my head what kind of line number we're looking at, but the problem, it's not a huge diff in that most of it's just that most of the functionality is contained to this file, but it does touch a lot of places.
Okay, thank you.
Okay, so that was the time really up signal. Thank you for your talk and engaged a lot of questions and perhaps too many questions time-wise. And yes, on behalf of the organization, present. So it's a traditional scarf with traditional writing on it. Okay, so more coffee now.
And if anyone did have follow-up questions, I'm happy to take those offline. So feel free to come find me.
start you, I guess. Well, welcome to the last talk of today with Juan and Losh, who is going to tell us everything about provisioning Linux boot images. And
Okay, thank you. Yeah, my name is Warner Losh. I work for Netflix, and today I'm going to talk about provisioning Linux boot images. So first, so you know what Linux boot is, I'm going to give a little bit of an intro to Linux boot. This is all wrapped up with UEFI and EDK2, so I'll talk a little bit about that. And then I'll talk a little bit about how you can develop the systems. Normally, when you're developing a Linux boot system, you want to put it into the NOR flash on a CPU. And I'll talk about what those are and the image formats and the tools you use to manipulate them and how do you put it all together. So I have a lot to cover. I won't cover anything in a lot of depth, but learning about Linux boot can be a bit of a steep mountain to climb in terms of all the things you need to know, and I hope this talk, and in addition to the other talks I've done on Linux boot, will help people that want to do it learn how to do it. So first, a quick recap. Linux boot at its basis is it assumes there's a CPU that boots. This boot, the CPU, then will load the firmware. And inside this firmware somewhere is a copy of Linux and the initRD. As you may know, the initRD is just the initial root file system for Linux. These usually are paired items, and they have some sort of scripting that figures out what to boot next. So the scripting will run. I guess I don't get Graph. The scripting will run, figure out what kernel to load, and load it. And so for the FreeBSD case, it runs loader.kexec and loads the FreeBSD kernel, and away we go. So today's talk will focus on this part of this chain. I'm not going to talk too much about, so you've booted FreeBSD from a Linux boot environment, because it's just like normal FreeBSD, and I won't talk too much about what happens before the firmware loads. So UEFI is the latest bootloader system that we have. Most people have a little bit of a familiarity with it, but most people probably don't know what goes on inside before the system comes up. So UEFI has kind of a pre-EFI phase, and that's a very thin layer that's responsible for turning on the memory, turning on the caches, maybe turning on a couple of other things that the Dixie layer, the device execution layer, which I'll talk about in a second, uses to do the rest of the booting. And then once that's set up the basic system, something called Dixie takes over. This is their device driver system. All the drivers that know how to read disks or do network stuff or type on, figure out what you typed on the keyboard, all of that, those are all DXE drivers. There's a Dixie initialization phase where they all initialize, and there's some ordering in that I'll maybe talk about a little bit later. And then comes the BDS phase, more algorithm, but this is just boot device selection. This is where it goes, oh, I have this NVMe drive here, it has these partitions. I'm going to read loader.efi off of that, off of the system partition I find on this NVMe drive, and then I'll jump to that, and that will load FreeBSD. And so those are basically the next two steps that happen. As people probably know, the ESP, the EFI system partition, is FAT formatted, and it has a number of different files on them under /EFI. And usually just has bootloaders, but sometimes it has some additional firmware or graphics that the bootloaders use or load before the OS comes up. And there's a lot of motherboard vendors that have EFI applications that will burn a new version of the boot ROMs, as another example of things that might be there. In the ASP, there's a number of defaults. Usually, the BDS looks at all of a whole bunch of boot variables and says, oh, it wants to boot this exactly and that exactly, and it does that. But when it can't find any of those, it falls back to the defaults. And there's just, this is just a quick chart of all of the different names that it might boot for all the different system architectures. So when you're developing Linux boot, and you want to go the whole 9 yards, and you're using UEFI, and there's a different talk if you're using Core Boot or one of the other bootloaders. But if you're using UEFI, what you do is you take the UEFI image that you get from EDK2, which is the Intel project. That's the open source version of UEFI that most vendors use and then add on. The images they produce have a lot of things in them that you might not need if you're using Linux boot. There's a network stack, a USB stack, a virtual I/O stack, all kinds of disks and file systems, all these things. And so what you would do is you would remove all of the stuff that you don't need and wind up with a more streamlined, streamlined image that has fewer things in it and has Linux doing the bulk of the network stack and the USB stack and all of that other stuff that makes it possible to squeeze everything into the tiny little boot ROMs you have. So before you go and try to read the boot ROMs and take them apart and put them back together, which is a very tedious and difficult process, you really need to have minimized Linux and a good initRD that you're going to run that'll do the booting. And the best way to do that is developing using the ESP. And here you add, the basic strategy is you add linux.efi, you add an initRD. UEFI has a funky shell language, so you write a short little shell script that runs Linux with a bunch of parameters that let it load the initRD, maybe tell it the console, maybe tell it the eventual root. I have an example, the script, which is one line as the second line up here, although it might be a little hard to read. I have uploaded my slides, by the way. I'll have a link to them at the end. Because there's a lot of commands that are, I'm going to go over quickly, but you might want to refer back to. Anyway, once Linux starts running, Linux has the ability to take the kernel and the UEFI bootloader and shove them together into one file. This is as if we took loader.efi and put the kernel on the end of it for a FreeBSD system. And this is the recommended way that kernel.org suggests that you run this. There's no EDK2 hacking, there's no UEFI slimming down needed. It lets you get the Linux kernel working on your hardware, because when you slim it down, you might have forgotten drivers you need. And it also lets you get the initRD script in the final form. Oftentimes you can debug most of it with a VM or a QEMU or something like that, but it always helps to be able to do the final debugging on actual real hardware before you try to do the slimming down that I'll talk about. So I'm going to talk a little bit about different ways to slim down the Linux kernel. What you do is you start with a clean tree. So if you don't have a clean Linux tree, you would make MR proper or Mr. proper to make it all neat and clean. And once you have that, you do make tinyconfig. If you have any architectural arguments, you would include those. And that creates a .config file. And that's what Linux uses to figure out what parts of Linux to include in the kernel. And tinyconfig is the most minimal config that you can have. There's a sister project to Linux called Linux Boot. And they have a repository which I have on a different slide. They have a repository that you can, on GitHub, that you can download stuff. And in this repository, they have a bunch of sample files for people to use to augment the tiny config. So I have a tiny config and I have a QEMU image and I'm running on ARM64. You take the tiny config and you take the snippet and put it on the end. And then you run make menu config, which will take all the bits that were added to the end and add them together. And if there's any additional configuration, it'll walk you through doing that. Once you've got the, all that set up, you save your config file and build Linux as normal. You know, these mechanics are fairly easy, but this is usually an iterative process. You have to do some sort of trial and error to figure out, oh, I forgot this, I forgot that. I need the PCI bus to talk to the NIC that's on the PCI bus, even though I had the NIC driver for it. You know, things like this that seem silly when it happens to you are just completely normal for this phase. Once you have everything working, you save the .config file away, and Linux has ways that you can update it in the future. One of the ways to do that is with make all no config. And that means answer no to all of the new options that Linux added since the last time it ran. And that'll let you take your minimal config, add all the required options, but not any of the optional options, so that you have a config file that you can then use to build a new version of the Linux kernel. And I also document a couple of ways that you can have this file be not .config, or you can compile to a different directory, as well as I also have pointers to their kbuild system up here, so that if you need to tweak different parameters, you can go and look through the documentation for those. You know, a lot of these are just a Google search away, but having them all in my slide deck, I'm hoping will make it easy for people to have a nice resource that they can just click on different things that they need. One thing to note is currently the Linux boot instructions call for an option called config EFI BDS. And this was needed once upon a time because Linux boot had patches to the Linux kernel that you needed to do this. They've moved all that functionality into a DXE driver that you can build from their repository. There's an issue here that the Linux boot guys asked me to include so that you would know what's going on if you wanted to get more information about it. Also, since the method I'm going to talk about is replacing the shell, there's no way to add command line arguments to that, and there's no way to tell the kernel what to do. So you have to do that through kernel config options. And the two kernel config options that are critical is config command line, so that you can set the console so that it'll print stuff out, and config init RAM FS source, so that you can give it that init RD that you can use to create the system. Also, when you go to build Linux, you build it, and I've been talking about linux.efi. You build it, and you go, okay, where's it at? And you do a find to try to find it, and it's not there. It's like, what the heck? I just built this. It should be there. I have all the right options, don't I? And you scratch your head, and then you check the documentation a little bit more carefully, and you find that it actually stores them in something called image or BZ image, depending on the architecture you're building for. BZ image is just a PE file that you can run directly from the EFI shell, that you can embed into the EFI firmware and whatnot. It was really confusing, and I thought that if I get confused, and I've been doing this, I got confused twice. The first time I did this about a year ago, and then when I was preparing the talk, it's like, hey, wait, where is that? And I realized, if I've thought of this twice, you know, it's got to be kind of a crazy thing. Also, when you're building Linux, Linux is best built on Linux. That is where everybody builds Linux and where it works. It's possible to build ARM 64 Linux on FreeBSD, There's only a couple of quick little hacks that you need to make that happen. If you really want to do that, I can provide them. And the kernel that results even seems to boot, which is a nice option. But for x86, Linux does a bunch of massaging the ELF file once for the loadable modules. And it has special tools to do that. And those special tools do not build on FreeBSD without a lot of crazy effort. And if you put that crazy effort in, you'll find that they don't run correctly. So it's best to build Linux on Linux. And a similar situation is the case on Mac OS. I ran into a very similar problem. It wouldn't build, it didn't have the right ELF libraries. I arranged to get those, and once I got those, it still didn't work in the same way as FreeBSD. So there's some bug, some problem that's common that I haven't had time to try to figure out. So I've just been building Linux on Linux, and that works really well. So I've been talking a lot about the initrd and different ways to deal with it. For people that don't know, this is just a CPIO file, maybe one that's been compressed, that Linux, the Linux kernel locates at boot and creates basically a giant RAM disk that has all these files on it that it then uses it as its initial root file system. Once it's done that, it will try to run a number of different binaries. Usually bin init is what I've been using. I think they even have bin systemd as one of the binaries that can run now, just because the takeover of systemd has been so complete. You don't have to do that if you're creating your own image. And this image is responsible in the Linux boot world for going out and finding the kernel that you want to boot, figuring out where it is on stable media, loading it in, and calling the system calls to load it into the Linux kernel, and then calling the special reboot function that tells Linux to reboot, and by the way, jump to that kernel that I loaded earlier. Some of the details about Linux boot and how all that works is in my previous talk. Also, one of the things I found confusing is that people use initrd and init ramfs interchangeably for the most part these days. A long time ago, in the 90s, initrd was the old and init ramfs was the new, and you had both options and you had to figure out based on the architecture which one to use, and now it's just all one thing. So if you don't want to create your own distribution for the initial boot, there's a couple of different projects out there. uroot has a set of utilities written in Go and that are compiled on the fly dynamically. It's the project that the Linux boot folks recommend, and it works pretty well. A lot of people also use BusyBox or RustBox or one of those other things as well to create the root. Since I've been trying to do things very minimally, I take the loader.kboot that I created for this project and package it up with loader.conf and all the Lewis scripts, and that's what I use for my initrd, so it's nice and small, and it fits, and it actually winds up being smaller than the Go image with just a couple of binaries for uroot. So that helps me fit in places that I wouldn't otherwise be able to fit in. There's another different ad hoc ways that you can create initrds. As long as it fits, then everything should be fine. And there's a couple of ways that you can use initrd. Basically, you have two choices. You can have them attached, where you compile the RAM disk into the kernel, or you could have it detached, and you have to tell the Linux kernel, hey, here's your RAM disk. And there's pros and cons to doing these. One file is nice, it's easy, you can move it around. You don't have to worry about a lot of other configuration or scripting to go along with it. But it also means that you have to change the kernel and the root file system at the same time. If you have them detached, you can change one but not the other, which might be advantageous if you've certified that the system runs with this kernel, and you just need to make a few fixes to your scripting as well. And which one you use largely depends on how you're deploying and which hassle you want to have, or which hassles you want to avoid, or which regulations you might need to deal with. I'm not going to go into this slide too much, but it talks about the way that I build my initRD for the Linux boot FreeBSD testing. And it's basically you create the image and then you run CPIO to create the initRD. Similarly, sometimes I like to have the kernel inside the RAM disk because for whatever reason, particularly when I'm developing on QEMU with the ESP, sometimes the virtual disks weren't working. So it was easier just to put it in the initRD and then read it out of that and then boot off of the NVMe drives that I was emulating. And this is a variation that shows how to do that. It'll be a much larger image. The first image was just under 1 megabyte. This image would be like 20 or 30 megabytes. Suitable for the ESP case, but since NOR flash is small, as I'll get into, maybe not so good for that. So this slide just pulls together different points that I had made earlier about using the UEFI shell to run Linux to boot everything off, and talks about the arguments that you will need to that. So backing up a little bit, to that first slide I showed you, when we boot the system on chip that's booting or the Intel processor that's booting usually boots a small bit of code that then does some very, very basic initialization, just enough to read the NOR flash and read memory, or read the firmware into memory. And then it goes through the different steps with UEFI and loads the bootloader and runs FreeBSD, or runs Linux, which then loads FreeBSD, which runs everything. And here I have different ways to construct an AArch64 image. Again, these are things I just put in the slide deck, so people had kind of an example, a working example of how to put it together on FreeBSD. But the basic thing is you create the image and then you use makefs and makeimage to create the file systems and the disk image respectively. And you can do it with UFS, you can do it with ZFS. Again, I have these commands here just as examples so that you don't have to go hunting for them and digging them up. So booting with QEMU. Once you have the image, that's what you'll want to do. You'll want to be able to test it and see what's going on, whether you're using the ESP thing or if you're using the slimmed down stuff later, you'll probably test it with, with QEMU. And I have some commands here that let you convert the ROM images that ship with QEMU to a version that QEMU can use to run the system. You usually want to have a copy because sometimes QEMU will write to this, like if you're setting EFI variables and so forth. You'll want to have a separate copy for each thing. And you can either just specify the one image, in which case it'll write it to that, or if you specify 2 images, it will write the EFI variables to the second image. So you can share the one larger image. So the file extension for the images that you're doing is .fd, and that will become important later. Here's a rather, starting to be a little bit of an eye chart for the command that I use to boot everything. Older versions of QEMU had VirtIO bugs, so I wound up having to have a VirtIO and an NVMe image of the same thing so that QEMU could read one and FreeBSD could read the other. If those bugs come back, you'll need to know that. But this sets up a system with no graphics and a serial console, which is the simplest system that you could possibly have. There are different additions that sometimes you might need to give to QEMU if you need to add this NVMe drive that I talked about. I have the instructions here. And sometimes you can use CPU Max, which will give you a little bit better performance than the A57. But sometimes using that will also encounter QEMU bugs. It's very QEMU version specific. I've bounced back and forth between those two options in the past year. So if you're trying to create a system, then you might need to know that as well. Also, the raw image doesn't need to necessarily be something you built. I used memstick images from the FreeBSD distribution to do a lot of the debugging because I wanted to be able to boot a stock unmodified FreeBSD kernel. We'll be able to do that with AMD 64. ARM64 required some rather extensive changes that I went into in a previous talk because of hardware errata with the interrupt controller. You couldn't reprogram it after it started, so the bootloader and the kernel have to agree on a bunch of stuff. And I talk about all that in a different talk, which I won't get into today. So one of the things that makes this project a little more challenging is most people don't have to deal with the NOR flash on your motherboard. It's something that comes from the manufacturer. Maybe if there's a bug, you'll update it once, but you don't really give it much of a thought. But this is where the boot images live, and this is where the boot images will need to be modified from. NOR ROM is used, it usually has less capacity, but is way more reliable than NAND. NAND is typically used for NVMe drives, for thumb drives and that sort of thing because it has a much bigger capacity, but it's also a much fussier technology, has higher errors, you need more error correction, you need to do more crazy things. NOR RAM, it's in like gigabytes or terabytes. NOR RAM is much smaller, it's usually measured in megabytes or tens or maybe 100 megabytes, but it's very reliable. So you don't need to do all the error correction that you would with NAND. So that's why it's favored by board makers because they can just read the memory off and put it into memory and they don't have to have all this error correction and their initial bootloaders can be much smaller. For laptops and some desktops, this memory is managed directly. You have little programs that you run that find the NOR ROM on one of the flash or the SPI controllers. SPI is just a different kind of bus that you can use that's like a high-speed version of I2C, which you might have heard of. But in servers, the BMC can manage the images that are in this. On servers, the BMC is just a second little computer that is a management engine that helps you manage the CPUs. It can turn power on and off. It can supply boot images and so forth. And one of the handy things it can do is also write this image so you don't have to get that working on your normal system. And if you screw up the image, even better, you can recover that as well. So this is a bit of an eye chart, and I don't expect people to look at it too extensively, but this is a block diagram of a ARM64 system, and it shows that the SPI is multiplexed between the main CPUs and the BMC, and the BMC up on the upper right has its own image that's managed separately. So, if you screw one up, you're not going to screw them both up. And just so that I had, for completeness, I included a motherboard for Intel. It also has the SPI flash, and it also has the BMC to manage things. I didn't find a good laptop block diagram to share. So The first thing that you want to do if you're trying to create a Linux boot image is to get what's called the FD image, and that's just the firmware device images. It's a term that is used in the UEFI standard to describe what these images are, and they're hierarchical. And there's a number of ways that you can get these images. If you're using QEMU, most QEMU packages have these images. If you're using a motherboard, sometimes you can, from some motherboard vendor, if you're lucky, you can download it from their website. And some motherboard vendors have special tools that you need to extract what's actually on the system. There's a couple of generic open source tools that I have referenced here. They usually work, but not always. They usually are more likely to work in the self-managed scenarios that I talked about, where you have a laptop or just a little desktop that doesn't have the auxiliary BMC inside of it. But when you start to get into the servers, sometimes the BMC, after it boots, it hides the boot ROMs to make it harder for adversaries to try to write to it. And so these tools won't work because they can't find the boot ROMs to extract. And if you're really desperate and can't find any other way, you can talk to your local electrical engineer who has or knows how to order all the hardware clamps that you can clamp down on top of the chip to read it directly, or to read it with a JTAG reader as well, if you're lucky, if the board has it. NOR flash is organized hierarchically. And it doesn't really matter too much. There's a couple of salient points. First of all, there's 2 dies here, and usually motherboard vendors have redundant copies, 1 in each die. So in case something goes wrong in one, they'll try to boot off of the other. And then the other thing to note is 64K is the size of what's called an erase block. When you're trying to replace part of the image, this is the smallest chunk that you can erase at a time, because with both NAND and NOR flash memory, in order to write to it, you have to erase it first. And then 512 or 256 bytes is the smallest page size that you can write to, and that corresponds to usually a sector. So inside of this NOR chip, there's the FD image. And the FD image has a bunch of BIOS headers that tell the BIOS how big it is and so forth. And then it has a nice little hierarchical file volume in it that has a number of different files. Most of them are PE fragments, but there's a few special ones that are also that are used for cryptographically signing these images. And inside each of the PE fragments, this will be important later when I talk a little bit about how to subset the image. Each PE fragment has a UUID that describes it uniquely. It has a text name, and then it has dependency data. That DXE, DepDex, or DepX is the dependency information. And then the PE data is just the image that you would create. That's where you would be putting linux.efi or loader.efi or whatever you wanted to put in here. I'm not going to read all these. There's over 100 of them. I use this to make the point that there's a lot of stuff in here. At least half of it you don't need. So clearly you're going to want to slim things down, because also there's usually just a few bytes left over, because motherboard makers like to put the most value into this and have the coolest, flashiest GUI, and you might not need that for your deployment. So the basic way that we do this, like I mentioned earlier, is we take the image, we remove the things we don't need, we replace the shell with linux.efi, and then we save it and burn it back to the flash. There'll be a few changes from the Linux image you made for the ESP to specify the command line console, maybe the root device to load, and also to compile in the initRD. The Linux boot folks have an experimental DXE driver that will let you separate them out and put them in nicely, but it only works on x86 and certain motherboards, and it generally, it's generally experimental right now, so it's a little easier just to package everything into one big chunk if you're wanting to do this today. So that was the alarm for questions, I guess. I just have a couple more slides, but basically there's a lot of stuff in here that you don't need that you can remove. This kind of lists a bunch of stuff. The Linux kernel has all these things if you need it. Most people aren't booting off of iSCSI. And it also, the EFI bootloader has a bunch of other stuff you don't. This is kind of a representative sizes. They range from about a megabyte down to 20 or 30K. And they take up 10 or 20 megabytes in the system. It's kind of crazy. But it also means that if you can remove these, there's room to be had for your Linux kernel. Since UEFI has to survive after Linux boots and provide runtime services, when you're looking at things to remove, don't remove anything that has runtime on it. But it's going to be a process of trial and error. And the UTK tool that people use to manipulate these images has a way that you can automate figuring out what's needed and what's not needed. Since this tool is written in Go, you can very easily install it with Go install and the GitHub repo here. And it also helps sometimes to have a copy of EDK2 around. And the UTK tool does a number of things that, to let you examine the system, it lets you validate it, and playing around with this, you can see how these things would be useful for different kinds of scripting that you would do. So generally, you would go through and you would remove a number of sections and then replace the shell with Linux and save it. And that's what this is trying to do. Unfortunately, you have to do it by UUID. So you're looking at the scan output to find the UUID that corresponds with the thing you want to remove, and you create a list. Or you use the Dixie cleaner. And what it does is you give it an image, and you say clean it, and you give it a test image. So it will test boot each one of the images with things removed, and if it boots, it'll keep it out. And if it doesn't boot, it'll put it back in and try again with other things removed. It's iterative, but it takes a while. It takes probably 200 or 300 test boots, each of which take 10 seconds, so it's half an hour or an hour if you're particularly unlucky. But it will result in the minimal set you'll need. This is really easy if all this is QEMU. It's a lot harder if each of the tests involved, burning to a remote system, seeing if the remote system booted or not, and then giving the answer back to the script. That can take days. So you want to have kind of it's like, oh, I'm just going to get rid of all the network drivers. You want to pre-do this so that you have a chance of doing everything. LinuxBoot.efi is the experimental thing that I was talking about that the Linux Boot project provides and is working on. And once it works, it'll be really cool because it will mean that you can take a stock Linux kernel and it will provide it with the command line arguments and stuff based on other things that are in the FV image. But I had trouble getting it to work. But the Linux Boot guys wanted me to put this on there as kind of a coming attraction when they reviewed my slides. So there's also something called UEFI tool, but that's GUI and graphical, but it's in kind of a state of chaos. It's good for looking at these and understanding the structure, but it's not so good for editing it. You have to use a really old version of it because they did a revamp to make it new and modern and somehow lost the ability to write images and the process. So it looks really cool, but it's not really useful anymore. So that was a lot in a hurry. Does anybody have any questions that I can answer? I have maybe 5 minutes for questions. Drew.
So like once you remove the vendors, the UEFI shell and GUI and all that stuff, how do you change something like, I don't know, like the memory interleaving, you know, that kind of thing?
So the question is, how do you change the, once you've taken all the vendor-specific stuff, how do you reload something new?
Like something that's in one of those menus, you know, that when you remove that whole menu system.
So if I remove the whole menu system, how do I change options like to control, for example, PCI lane bifurcation between the different slots?
Memory interleaving is what I was saying.
Generally, you can't. In the general case, you can't because those are all vendor specific. A lot of vendors, though, will document that the configuration for all of those things are controlled by different EFI variables, and you can change the EFI variables from the command line in FreeBSD or Linux and change it that way, which is very tedious and error prone. If you need to do that, this might not be the thing for you, or you might need to find other things to remove. So it is a trade-off. Or you might be able to flash an image that lets you change it, make the changes, and then reflash your Linux boot image with the BMC, although that gets kind of scary and dicey, as you might imagine.
Thank you.
Okay, are there other questions that I can help you with? Or, yes, back here, I don't know your name, I'm sorry.
Yeah, maybe it's a silly question, but what would be missing to replace Linux by FreeBSD? Probably a kexec, kboot, and...
So your question is, why Linux? Why not put FreeBSD in the boot ROM? FreeBSD doesn't have kexec right now. So if you could pick the exact right FreeBSD kernel, it could work. And I've done that. So I'm being gonged off the stage, evidently. Oh no, there's 3 minutes of questions left. So not completely yet. It's not, I need a second gong. Are there any other questions that people have that I can answer? I guess not. Okay, thank you, everybody.
So, well, yeah, thank you for your talk. And as a token of appreciation is a gift from the committee. So it's from the committee. So it's
thank you.